The universe is a place of endless wonder, filled with mysteries so strange they seem ripped from the pages of science fiction. Imagine a signal from deep space so powerful it stunned scientists, or a star that flickers like a broken streetlight, hinting at forces we can't yet explain. Picture entire galaxies being dragged toward an unseen cosmic monster, or an interstellar visitor tumbling through our solar system, its origins and purpose shrouded in secrecy. These aren't scenes from a blockbuster movie, they're real phenomena happening right now in the cosmos, and we've barely scratched the surface of understanding them. Today, we're diving into 50 of the most bizarre enigmas the universe has to offer, from invisible forces shaping reality to celestial objects that defy all logic. Some might be the key to unlocking the secrets of existence itself, while others could rewrite everything we know about physics. So buckle up and open your mind, because by the end of this journey, you'll never look at the night sky the same way again. And who knows, one of these mysteries might just hold the answer to humanity's biggest question: are we truly alone? Stick around, the cosmos has surprises you won't see coming. Now, let's kick things off with a cosmic mystery that sent shockwaves through the scientific community: the infamous WOW signal. Picture this: a quiet night at Ohio State University's Big Ear radio telescope in August 1977, when suddenly, an astronomer named Jerry Amon spots something extraordinary. A burst of radio waves so intense, so unexpected, that it stands out like a scream in the silence of space. The signal lasted just 72 seconds, but its intensity was off the charts, 30 times stronger than the background noise of the cosmos. And here's the kicker: it seemed to come from a region near the constellation Sagittarius, with no natural explanation that fit the bill. Amon was so stunned by the data that he circled it on the printout and scribbled, "Wow." Next to it, a name that stuck. But what made this signal so special? For starters, it hit a frequency of 1420 MHz, a quiet band where natural cosmic noise is minimal. This is significant because it's also a frequency scientists had theorized aliens might use to communicate, known as the hydrogen line. Add to that the signal's narrow bandwidth, another hallmark of potential artificial origin, and you've got a recipe for endless speculation. Decades later, the WOW signal remains one of astronomy's greatest unsolved puzzles. Some argue it was a one-time fluke, a passing comet, or a glitch in the telescope. Others point out that no comet was known to be in that exact spot at the time, and no human-made satellites were broadcasting at that frequency. Even more intriguing, despite countless efforts to listen for a repeat signal, the cosmos has never spoken like that again. So, was it a fleeting hello from an advanced civilization, or just a cosmic oddity we still don't understand? The debate rages on, but one thing's certain: the WOW signal reminds us that the universe is full of surprises, and sometimes the most tantalizing clues leave us with more questions than answers. And if you think that's wild, just wait, we're only getting started. Now, let's turn our attention to something even more elusive than a mysterious radio signal: dark matter. Imagine looking at the night sky and realizing that everything you see, the stars, the galaxies, the shimmering cosmic dust, accounts for less than 5% of the universe's total mass. The rest, a vast, invisible presence we can't see, touch, or directly detect, yet it shapes the very fabric of reality. That's dark matter, the enigmatic substance making up roughly 27% of the cosmos, and its existence is one of the most profound mysteries in modern science. The story of dark matter begins with a puzzle: galaxies spinning faster than they should. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving so quickly they should have flown apart. But they didn't. Something unseen was holding them together with its gravitational pull. Decades later, Vera Rubin's observations of spiral galaxies confirmed this. stars at the edges orbited just as fast as those near the center, defying the laws of gravity as we knew them. The only explanation, an invisible mass weaving an unseen web of gravity that keeps galaxies intact. So what exactly is dark matter? Here's where things get tricky. We know it's not made of atoms, otherwise it would interact with light and we'd see it. It doesn't absorb, reflect, or emit any form of electromagnetic radiation. It's utterly transparent, yet its gravitational effects are undeniable. Think of it like the wind. You can't see it, but you feel its force. Entire galaxies move under its influence, and even light bends around it, a phenomenon called gravitational lensing. Scientists have proposed countless theories to explain dark matter. Some believe it's made of weakly interacting massive particles, or WIMP hypothetical particles that barely interact with normal matter except through gravity. Others suggest actions, ultra-light particles born in the early universe. There's even the radical idea that our understanding of gravity itself is flawed, and dark matter doesn't exist at all, a theory known as modified Newtonian dynamics or MN. But despite decades of searching, no experiment has definitively detected dark matter particles. Underground labs, particle colliders, and space telescopes have all come up empty-handed, deepening the mystery. Why does this matter? Because dark matter isn't just a cosmic curiosity, it's the scaffolding of the universe. Without it, galaxies wouldn't have formed, and the cosmos as we know it wouldn't exist. Its gravitational pull shaped the distribution of galaxies, and it continues to dictate the fate of the universe itself. Yet, for something so fundamental, it remains frustratingly out of reach. So while we may not know what dark matter is, its presence is undeniable. It's a reminder that the universe is far stranger and more mysterious than we can imagine. And just like the wow signal, it leaves us with more questions than answers for now. But as we'll soon see, dark matter isn't the only invisible force shaping the cosmos. Just when we thought the universe couldn't get any stranger, along comes dark energy, a force so baffling it makes dark matter seem almost ordinary. Picture this: not only is most of the cosmos invisible, but the little visible part we do see is being pushed apart at an ever-increasing speed. That's dark energy in action, the mysterious driver behind the universe's accelerated expansion, and it's rewriting the rules of physics as we know them. The story of dark energy begins with a bombshell discovery in the late 1990s. Two teams of astronomers were studying distant supernova exploding stars that act as cosmic mile markers to measure how the universe's expansion had changed over time. They expected to find the expansion slowing down, pulled by gravity's relentless tug. Instead, they found the opposite. The universe wasn't just expanding, it was speeding up, as if some invisible force was overpowering gravity itself. The shock was so profound, it earned the researchers a Nobel Prize. So what exactly is dark energy? Here's the unsettling truth: we don't know. Unlike dark matter, which at least reveals itself through gravity, dark energy is even more elusive. It doesn't clump around galaxies or bend light. Instead, it seems to be a property of space itself, a sort of anti-gravity woven into the fabric of the cosmos. One leading theory suggests it's the cosmological constant, a term Einstein once added to his equations and later called his biggest blunder to describe a repulsive force inherent to empty space. But when calculated, the predicted strength of this force is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. In other words, our best guess is spectacularly wrong. Another idea is that dark energy is a dynamic field, like an invisible fluid filling space but with negative pressure. Think of trying to push a balloon underwater, only for it to expand faster the harder you press. Some theories even propose that our universe is colliding with an unseen parallel dimension, or that Einstein's theory of gravity breaks down on cosmic scales. Yet every explanation comes with glaring holes, leaving scientists scrambling for answers. Why does this matter? Because dark energy isn't just a puzzle, it's the dominant force in the universe, making up a staggering 68% of its total energy. It's deciding the ultimate fate of everything. If it continues unchecked, it could tear galaxies apart, leaving the cosmos cold, dark, and empty, a fate called the Big Freeze. But if it fluctuates or strengthens, the universe could face a catastrophic Big Rip, where even atoms are torn asunder. Dark energy challenges everything we thought we knew. It defies detection, resists explanation, and forces us to confront how little we understand about the universe. Yet it's also a thrilling reminder that the cosmos still holds profound secrets, and the next great discovery might be just around the corner. Speaking of cosmic secrets, let's turn to another enigma, the fleeting, powerful blasts known as fast radio bursts. Now, let's dive into one of the most electrifying mysteries in modern astronomy, fast radio bursts. Imagine tuning your radio to static, only to catch a blip of sound so powerful it outshines entire galaxies. But lasting just a fraction of a second, that's an FRB in a nutshell. These cosmic flashes pack more energy than the sun emits in 80 years, yet vanish before we can blink. The first fast radio burst was discovered in 2007, buried in archived data from Australia's Parkes Observatory. Astronomers initially dismissed it as a glitch until more appeared. Today, we've detected hundreds, some repeating like clockwork, others flaring once and disappearing forever. Their unpredictability is maddening. One might erupt every 16 days while another strikes at random, like a cosmic Morse code with no clear sender. So what's behind these bursts? The leading suspect is magnetars, neutron stars with magnetic fields so intense they could wipe a credit card clean from halfway across the Milky Way. When these stars undergo starquakes or magnetic eruptions, they might unleash FRBs like sparks from a live wire. In 2020, a magnetar in our own galaxy emitted an FRB-like signal, bolstering this theory. But not all bursts fit neatly into this box. Some repeat with bizarre precision, while others arrive with patterns that defy known physics. Then there's the extraterrestrial angle. Could FRBs be alien beacons or even propulsion systems? The repeating ones, like FRB 1212, pulse with a regularity that's almost artificial. Scientists once traced an FRB to a spiral galaxy 3 billion light-years away, precisely the kind of place we'd expect advanced civilizations. But before you picture interstellar radio stations, consider this: nature is often stranger than sci-fi. The energy required for an alien transmitter would dwarf Earth's total power output, making it an implausible but irresistible idea. What makes FRBs invaluable isn't just their mystery, it's their utility. As these bursts race across the universe, they interact with the sparse matter between galaxies, allowing us to weigh the cosmos' missing atoms. They're cosmic yardsticks helping map the universe's structure. Yet every answer raises new questions. Why do some FRBs seem to come from dead galaxies? How can a single source produce bursts with wildly different energies? One thing's certain: fast radio bursts are more than cosmic fireworks. They're probes into the universe's most extreme environments, challenging our understanding of physics and even sparking conversations about life beyond Earth. And just when we think we've got them figured out, they surprise us again, proving the cosmos still holds cards it hasn't shown us. Which brings us to our next enigma, a star whose flickers sparked whispers of alien megastructures. Now let's shift our gaze to a star that refuses to play by the rules. Meet Tabby's star, officially known as KIC 8462852, a celestial oddball that's baffled astronomers with its unpredictable flickers. Unlike the fleeting blips of fast radio bursts, this star's mystery unfolds in slow motion, dimming by as much as 22% at irregular intervals, as if something colossal is passing in front of it. Discovered in 2015 by citizen scientists sifting through Kepler Space Telescope data, Tabby's star quickly became a cosmic sensation. Most stars dim by tiny fractions when planets transit, but this one's drops were dramatic and erratic. No known natural phenomenon, not planets, not comets, not even interstellar dust, could fully explain the dips. That's when the speculation erupted. Could this be evidence of alien engineering? Enter the Dyson sphere hypothesis. Proposed by physicist Freeman Dyson in the 1960s, the idea suggests advanced civilizations might build vast energy-harvesting structures around stars. Tabby's star's irregular dimming seemed to fit the bill. Imagine a swarm of solar panels, each the size of a continent, orbiting the star in a chaotic ballet. It was a tantalizing thought, but science demands evidence, not just imagination. Further observations revealed a twist. The star wasn't just dimming erratically, it was also gradually fading over time. By 2018, studies showed its brightness had dropped by 14% over a century. This long-term dimming pointed to dust, not megastructures. Dust particles, unevenly distributed, could explain both the sudden dips and the slow decline. Yet even this explanation left gaps. Why was the dust behaving so strangely? And why did some wavelengths of light dim more than others? Then came the most compelling clue. In 2021, astronomers caught the star red-handed mid-dip. The way different colors of light were blocked pointed squarely to dust grains, tiny, porous, and possibly rich in carbon. No alien megastructures, just cosmic debris. But don't write off the mystery yet. This dust isn't like the uniform haze around young stars. It's clumpy, unpredictable, and possibly linked to a recent planetary collision or a swarm of icy bodies breaking apart. Tabby's star teaches us a vital lesson about cosmic curiosity. Sometimes the most extraordinary explanations, like alien engineering, are the ones that capture our imagination first. But nature, as always, proves more inventive than fiction. The real story here isn't just about dimming starlight. It's about how anomalies push science forward, forcing us to refine our tools and question our assumptions. And while dust might not be as thrilling as Dyson spheres, the puzzle of its origin still keeps astronomers up at night. Which brings us to our next cosmic conundrum, a gravitational giant lurking in the shadows of our own galaxy. Now, let's journey deeper into the cosmic unknown, where an invisible force tugs at galaxies like a puppeteer pulling strings. Hidden behind the curtain of our own Milky Way lies one of the universe's most puzzling gravitational mysteries, the Great Attractor. Imagine this: every galaxy in our cosmic neighborhood, including our own, is being drawn toward a point in space we can't even see directly. It's as if the universe has set its sights on a secret rendezvous, and we're just beginning to decipher the invitation. This enigmatic pull was first noticed in the 1970s when astronomers mapped the motion of galaxies and realized something was amiss. The Milky Way, along with thousands of other galaxies, is racing toward a region of space roughly 250 million light-years away at a staggering speed of over 600 kilometers per second. But here's the twist. The Great Attractor sits in a part of the sky obscured by our galaxy's dense disk of stars, gas, and dust, a zone astronomers call the zone of avoidance. It's like trying to spot a lighthouse through a thick fog. Early theories suggested the Great Attractor might be a single, massive object, a supercluster of galaxies with gravity powerful enough to bend the motion of everything around it. But as technology advanced, so did our understanding. In the 1990s, observations revealed that the Great Attractor isn't alone. It's part of an even larger structure known as the Laniakea supercluster, a cosmic web of hundreds of thousands of galaxies spanning 500 million light-years. Within this vast network, the Great Attractor acts as a gravitational anchor, pulling everything toward its dense core. Yet the mystery deepens when we ask, what lies at the heart of this pull? The answer isn't just one massive cluster, but a complex interplay of dark matter, galaxies, and superclusters. Dark matter, that invisible scaffolding of the universe, is thought to weave through this region in dense filaments, amplifying the gravitational tug. Even so, the observed motion of galaxies suggests there might be something even more massive lurking beyond the Great Attractor. Perhaps an undiscovered supercluster or a colossal concentration of dark matter. The challenge of studying this region isn't just its hidden location. The zone of avoidance blocks visible light, forcing astronomers to rely on other wavelengths like infrared and radio to peer through the cosmic veil. Projects like the Parkes Observatory's Hydrogen Sky Survey have slowly pieced together a clearer picture, revealing galaxies and structures once lost in the glare of the Milky Way. Each discovery chips away at the mystery, showing that the Great Attractor isn't a lone giant but a node in the universe's grand design. What makes this cosmic tug of war so fascinating isn't just the hidden mass, it's what it reveals about our place in the universe. We're not stationary observers but passengers on a galactic voyage, caught in a flow older than Earth itself. The Great Attractor reminds us that even the grandest structures in the cosmos are part of something larger, a reminder of how much we've yet to explore. And as we unravel its secrets, we're left with another tantalizing question. What other invisible forces are shaping the universe around us? That's a mystery we'll keep chasing, just beyond the edge of the Milky Way's shadow. But the cosmos has more surprises in store. Next, we confront a paradox that has puzzled scientists for decades: why the universe seems so silent in the face of countless stars and planets. Now, let's shift our gaze from the unseen forces tugging at galaxies to a question that has haunted humanity for generations. Where is everybody? On a clear night, when you look up at the countless stars dotting the sky, it's almost impossible not to wonder, are we truly alone? The universe is unimaginably vast, with hundreds of billions of galaxies, each hosting hundreds of billions of stars. Statistically, the probability of alien life seems overwhelming. And yet, despite decades of searching, we've found no definitive evidence. This glaring contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" The paradox hinges on a simple but profound puzzle. Given the age of the universe and the sheer number of habitable planets, intelligent civilizations should have arisen long before us. By now, they should have spread across the galaxy, leaving traces we can't possibly miss. So why does the cosmos remain so silent? One of the most unsettling answers is the Great Filter theory. The idea is that somewhere along the path from simple chemistry to spacefaring civilization, there's a nearly insurmountable barrier, a filter, that wipes out life before it can become advanced enough to be detected. The chilling part, we don't know if we've already passed the Great Filter or if it still lies ahead of us. If it's behind us, say, in the unlikely event of life emerging in the first place, then humanity might be one of the rare exceptions destined to explore the stars. But if the filter is ahead, like self-destruction through nuclear war, climate collapse, or some unforeseen catastrophe, then our future could be grim. This theory forces us to confront the fragility of our own existence. Are we the lucky survivors, or are we unknowingly racing toward our own extinction? Other explanations for the Fermi Paradox range from the optimistic to the bizarre. Maybe advanced civilizations are deliberately avoiding us, adhering to some cosmic prime directive. Or perhaps they've moved beyond the need for physical expansion, existing in digital realms we can't perceive. There's even the haunting possibility that intelligent life inevitably destroys itself, a pattern repeating across the universe. Then there's the zoo hypothesis, which suggests Earth is being intentionally isolated, like a nature reserve, observed but not interfered with, or the dark forest theory, which paints a universe where civilizations stay hidden, fearful of attracting hostile attention. Each of these ideas offers a different lens on our cosmic solitude, but none provide definitive answers. What makes the Fermi Paradox so compelling isn't just the lack of evidence, it's what it reveals about our place in the cosmos. Every silent radio telescope, every empty exoplanet survey forces us to reconsider our assumptions. Are we special or are we doomed? The search continues, but for now, the universe keeps its secrets close. And as we listen for whispers in the void, we're left with one undeniable truth. The silence speaks volumes, but space has more mysteries to unveil. Next, we'll examine an enigmatic object orbiting Earth, one shrouded in myth and conspiracy. Turning from the eerie silence of the Fermi Paradox, let's dive into a mystery that's been orbiting Earth literally. High above our planet, whispers of an ancient alien satellite have captured imaginations for decades. Meet the Black Knight, a shadowy object said to be a relic of extraterrestrial technology, silently watching us for thousands of years. But where did this story come from, and is there any truth to it? The tale begins in the late 1950s, when newspapers reported unusual radio signals supposedly echoing from space. Some claimed these were intercepted by amateur radio operators, while others insisted they came from a mysterious satellite of unknown origin. The timing was crucial. This was the dawn of the space age, just before humanity launched its first artificial satellite, Sputnik. The idea that something already orbited Earth sent chills through the public. Then came the visual claims. In 1998, during a space shuttle mission, photographs appeared to show a strange, jagged object floating near Earth. Conspiracy theorists pounced, declaring it proof of the Black Knight. The images, though, were far from conclusive. Experts identified them as space debris or thermal blankets lost during earlier missions. But the legend had already taken flight, fueled by grainy footage and a hunger for cosmic secrets. What's fascinating isn't just the myth, it's how it evolved. Some say the Black Knight dates back to Nikola Tesla, who in the early 20th century claimed to have picked up repeating signals he believed were extraterrestrial. Others tie it to ancient astronaut theories, suggesting it's a relic from a long-lost civilization or even a gift from alien visitors. Pop culture embraced it too, with references in films, TV shows, and music, cementing its place in modern folklore. Science, however, tells a quieter story. Astronomers explain that the Black Knight is likely a combination of misidentified objects, space junk, discarded satellite parts, or even natural phenomena like meteors reflecting sunlight. The International Space Station, for instance, often catches flaring debris that can look otherworldly to the untrained eye. Radar anomalies and optical illusions add to the confusion, creating the perfect recipe for an enduring mystery. Yet, the Black Knight's legacy isn't just about debunking myths. It's a mirror reflecting our fascination with the unknown. In a universe full of genuine enigmas, this one reminds us how easily stories can eclipse facts and how the line between curiosity and credulity can blur. So while the satellite itself may not be alien, the questions it raises about discovery, skepticism, and our place in the cosmos are undeniably real. But space has even stranger tales to tell. Up next, we'll journey to the heart of a galactic powerhouse where light defies comprehension. Leaving behind the myths of Earth's orbit, let's travel billions of light years into the depths of space where reality outshines even the wildest fiction. Imagine a beacon so powerful it outshines entire galaxies, fueled by an insatiable cosmic predator. Welcome to the realm of quasars, the universe's most luminous objects, turning the darkness of deep space into a blazing spectacle. At their core, quasars are supermassive black holes, but not the quiet, lurking kind. These are monsters in the middle of a feast, swallowing vast amounts of gas, dust, and even entire stars. As material spirals inward at nearly the speed of light, friction heats it to millions of degrees, creating a swirling disk of white-hot plasma. The energy released is unimaginable. Some quasars emit light thousands of times brighter than the Milky Way, all from a region no larger than our solar system. Their brilliance makes them cosmic lighthouses, visible across staggering distances. The first quasar discovered, named 3C273, was spotted in the early 1960s. At first, astronomers thought it was a nearby star, but its spectrum told a different story. The light was redshifted, meaning it came from the edge of the observable universe over 2 billion light-years away. Suddenly, scientists realized they were seeing the universe in its violent youth, when black holes and galaxies were just beginning to shape the cosmos. What makes quasars even more fascinating is their role as time capsules. Because light takes time to travel, the quasars we see today are snapshots of the universe when it was just 1 or 2 billion years old. They reveal an era of chaos where black holes grew to colossal sizes by devouring everything around them. Some theories suggest these early behemoths actually paved the way for galaxies to form, their gravity pulling in the raw materials that would eventually become stars. Yet quasars aren't just relics of the past. Recent discoveries show they can be surprisingly dynamic. Some flicker in brightness over days or even hours, hinting at turbulent processes near the event horizon. Others shoot out jets of particles at nearly light speed, spanning millions of light years and carving through intergalactic space like cosmic blowtorches. These jets are so powerful they can influence the formation of entire galaxy clusters, proving that quasars aren't just bright, they're architects of the large-scale universe. But perhaps the most humbling thought is this: every quasar we see is a glimpse into our own galaxy's past. The Milky Way's central black hole, Sagittarius A star, is quiet now. But billions of years ago, it might have been a quasar too, its fury shaping the stars and planets that would one day give rise to us. So while quasars seem like distant oddities, they're actually part of the same story that led to Earth, a story still being written in the fire of these cosmic powerhouses. And speaking of fire, our next journey takes us to a place where time and space twist into something even stranger. Now, shifting our gaze from distant cosmic furnaces to the silent paths of our own solar system, we encounter a mystery that puzzled scientists for decades. It's the strange case of the Pioneer spacecraft, twin probes that defied the laws of physics in ways no one could initially explain. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were humanity's first emissaries to the outer planets, trailblazing paths toward Jupiter and Saturn. But as they ventured farther from the Sun, something peculiar happened. Both probes began slowing down ever so slightly, as if an invisible hand was gently tugging them back toward the inner solar system. This tiny but persistent deceleration became known as the Pioneer anomaly, a deviation so small it amounted to just a fraction of a nanometer per second squared, yet it stubbornly refused to vanish. For years, this anomaly haunted physicists. Some wondered if it hinted at flaws in Einstein's theory of relativity. Others speculated about unseen dark matter or even exotic new forces acting across the solar system. The most tantalizing possibility that we'd stumbled upon a crack in our understanding of gravity itself. But science has a way of untangling even the knottiest puzzles. Decades of meticulous analysis revealed a far humbler culprit: heat. The probe's radioactive power sources, called RTGs, emitted a faint but constant stream of thermal radiation. As this heat radiated unevenly from the spacecraft, it created a tiny recoil force enough to nudge the probes off their expected trajectories. It wasn't a cosmic mystery after all, just the subtle physics of warmth in the vacuum of space. Yet the Pioneer anomaly's legacy endures. It taught scientists an invaluable lesson about the devilish precision required in deep space navigation. Even the faintest forces, like the pressure of sunlight or the whisper of thermal radiation, can add up over billions of miles. Modern missions like New Horizons now account for these effects with exquisite care, thanks to Pioneer's unexpected detour. And while the anomaly's explanation turned out to be ordinary, its journey was anything but. For 30 years, it stood as a reminder that space still holds surprises, even in our own celestial backyard. Sometimes, the universe's greatest mysteries aren't found in distant quasars or dark matter, but in the quiet, unresolved details closer to home. Speaking of home, our next stop takes us even farther into the unknown, where an interstellar visitor left scientists scratching their heads. Now, turning our attention from the familiar paths of our solar system to the great cosmic highway between the stars, we encounter one of the most tantalizing visitors ever observed, Oumuamua. This mysterious object didn't just pass by, it left scientists questioning everything they thought they knew about interstellar travelers. First spotted in October 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua, meaning scout or messenger from afar in Hawaiian, was unlike anything astronomers had seen before. For starters, it wasn't from around here. Its trajectory and speed made it clear. This was our first confirmed visitor from another star system, hurtling through space at nearly 200,000 miles per hour. But the real mystery wasn't just where it came from, it was what it was. Oumuamua's shape defied expectations. Most asteroids and comets are roughly round or lumpy, but this thing was different. Based on the way its brightness fluctuated as it tumbled through space, scientists estimated it was at least 10 times longer than it was wide, something like a cosmic pencil or a flattened pancake. If you've ever imagined an interstellar spaceship from science fiction, well, Oumuamua's shape wouldn't look out of place. Then came the real head-scratcher, its acceleration. As it zoomed away from the sun, something pushed it ever so slightly faster, like an invisible engine giving it a little kick. Comets do this when their icy surfaces heat up and release gas, but Oumuamua didn't show any signs of the telltale tail or gas cloud. No visible outgassing, no dust, nothing. So what was propelling it? This is where things got wild. Some scientists, like Harvard's Avi Loeb, floated the idea that Oumuamua might not be a natural object at all. Could it be an alien probe, perhaps a discarded piece of technology, or even a solar sail propelled by starlight? The possibility, however slim, electrified the public imagination. But others argued for less exotic explanations. Maybe Oumuamua was a comet after all, just one made of unusual materials that left no visible trail. Or perhaps its strange acceleration came from hydrogen ice vaporizing, a process too subtle for our telescopes to detect. The debate raged on with no definitive answer. What makes Oumuamua so fascinating isn't just the mystery of its identity, but what it represents. It's proof that interstellar objects pass through our solar system more often than we ever realized. Some may even be hiding in plain sight, masquerading as ordinary asteroids until we look closer. Future telescopes like the Vera Rubin Observatory could uncover dozens more, each one a potential clue to the building blocks of other star systems. Oumuamua may be long gone, streaking through the void toward parts unknown, but its legacy lingers. It reminded us that the cosmos is full of surprises, and sometimes the most profound discoveries come in the strangest packages. And speaking of strange packages, our next mystery takes us to one of the eeriest places in the universe, a void so vast and empty, it challenges our understanding of space itself. Now, shifting our gaze from the fleeting mysteries of interstellar travelers to the vast, uncharted emptiness between the galaxies, we arrive at one of the universe's most unsettling enigmas, the Boötes Void. Dubbed the Great Nothing, this staggering cosmic desert stretches an almost incomprehensible 330 million light-years across, making it one of the largest known voids in existence. Yet, despite its mind-bending scale, the Boötes Void isn't entirely empty. Scattered across its expanse are a mere 60 or so galaxies, far fewer than the thousands we'd expect in a region that size. Discovered in the 1980s by astronomer Robert Kirshner and his team, the Boötes Void defies our understanding of cosmic structure. The universe, after all, isn't supposed to be this lopsided. According to the standard model of cosmology, matter, both visible and dark, should be distributed somewhat evenly, like foam in a bubble bath. But the Boötes Void isn't just a gap, it's a gaping hole, a place where the universe forgot to put galaxies. So what could have caused such a colossal emptiness? One theory suggests it's the result of smaller voids merging over billions of years, like soap bubbles combining into one giant cavity. Another, more unsettling idea is that the void might be evidence of an ancient collision with a parallel universe, a cosmic bruise left behind by something beyond our observable reality. Then there's the possibility of a supervoid, a region where dark energy dominates so completely that it repels ordinary matter, pushing galaxies away like a force field. But the Boötes void isn't just a scientific curiosity, it's a puzzle that challenges the very foundations of cosmology. If voids this large exist, they shouldn't, at least not in the numbers predicted by our current models. Their existence hints that either our understanding of dark energy is flawed, or that the universe is far stranger, far more uneven than we ever imagined. For now, the Boötes void remains a silent giant, a cosmic question mark hanging in the dark, but every unanswered question is an invitation to explore further, to look deeper. And as our telescopes grow more powerful, who knows what other voids, or what other secrets might reveal themselves. Speaking of cosmic curiosities, our next phenomenon takes us from the emptiness between galaxies to an unexplained boundary much closer to home. A place where the solar system's icy debris suddenly vanishes as if guarding a hidden secret. Now, as we turn our attention from the vast emptiness of the Boötes void to the edges of our own solar system, we encounter a mystery much closer to home, the Kuiper Cliff. This strange boundary, located roughly 50 astronomical units from the Sun, marks a dramatic and unexplained drop in the number of icy objects floating in the Kuiper belt, the distant ring of frozen debris left over from the solar system's formation. Imagine the Kuiper belt as a cosmic junkyard, filled with comets, dwarf planets, and icy fragments stretching from Neptune's orbit out into the darkness. Astronomers expected this region to gradually thin out the farther you go, but instead, at around 50 astronomical units, the number of objects suddenly plunges as if someone built an invisible wall. This sharp cutoff, known as the Kuiper Cliff, defies our expectations. Why does this matter? Because the Kuiper belt isn't just a collection of space rocks, it's a fossil record of our solar system's early days. Its structure should reflect the gentle pull of gravity over billions of years, not abrupt edges. So when scientists first noticed this steep decline in objects beyond 50 astronomical units, they knew something unusual was at play. One leading theory suggests the presence of an undetected planet lurking far beyond Pluto. This hypothetical world, sometimes called Planet 9, might be massive enough to gravitationally clear out the outer Kuiper belt, sweeping away smaller objects or flinging them into distant orbits. If real, Planet 9 could be up to 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun in a slow, wide loop. But there's another possibility, something even more dramatic. The Kuiper Cliff might be evidence of a violent event in our solar system's past, like a close encounter with a passing star. Such an encounter could have stripped away the outer Kuiper belt, scattering its objects into interstellar space. Or perhaps the early Sun formed in a crowded star cluster, where frequent gravitational tugs from neighboring stars reshaped the distant debris. The mystery deepens when we consider that similar patterns appear in other planetary systems, hinting that this phenomenon might not be unique to us. Yet for now, the Kuiper Cliff remains one of the solar system's most puzzling features, a silent reminder that even in our own cosmic backyard, we're still uncovering surprises. As we peer into this frozen frontier, we're left with more questions than answers. But that's the thrill of exploration. Every boundary we cross leads to new mysteries waiting to be solved. And speaking of cosmic anomalies that challenge our understanding, our next stop takes us even deeper into the unknown, where the very fabric of the universe itself seems to hold a controversial secret. But before we dive into the next cosmic enigma, let's shift our focus from the strange edges of our solar system to the very foundations of the universe itself. What if I told you that the afterglow of the Big Bang might hold a clue that shakes our understanding of reality? Enter the axis of evil, one of the most debated oddities in modern cosmology. This isn't about some galactic supervillain, it's a mysterious pattern hidden in the cosmic microwave background, the faint echo of radiation left over from the universe's birth. Scientists expected this ancient light to be randomly distributed, a chaotic snapshot of the infant cosmos. But when they mapped it, they found something unsettling, a strange alignment of hot and cold spots that seemed to line up with the plane of our solar system. Why is this so controversial? Because according to the Big Bang theory, the universe should have no preferred direction, no special axis. The cosmos is supposed to be isotropic, meaning it looks the same in every direction. But the axis of evil suggests the opposite, hinting that our solar system might somehow be linked to the universe's largest scale structure. It's like finding your fingerprints on a crime scene from billions of years before you were born. Some researchers argue this alignment is just a statistical fluke, a cosmic coincidence in the data. Others propose wilder explanations, like the influence of a parallel universe or a flaw in our current physics. Then there's the unsettling possibility that we're seeing evidence of pre-Big Bang structures, relics from a time before time as we know it. The stakes couldn't be higher. If the axis of evil is real and not an illusion, it could force us to rewrite textbooks. Maybe the universe isn't as random as we thought. Or perhaps our solar system occupies a bizarrely privileged position in the cosmos, defying everything we know about cosmic humility. As the debate rages on, one thing is certain: the axis of evil reminds us that even our most cherished theories about the universe are provisional. Every time we think we've figured it all out, the cosmos throws us a curveball. And with that humbling thought, we're ready to confront another celestial oddity, one where geometry defies nature's usual chaos. Switching our gaze from the cosmic mysteries hidden in ancient light, let's turn toward a celestial spectacle that looks almost too perfect to be natural: the Red Rectangle Nebula. Nestled about 2,300 light-years away in the constellation Monoceros, this glowing structure defies the usual chaos of space with its striking symmetry. Unlike most nebulae, which sprawl in chaotic, cloud-like formations, this one appears as a near-flawless geometric masterpiece, its crimson hues framing a shape so precise it could pass for an interstellar monument. So what creates this cosmic artwork? The leading theory points to a pair of aging stars locked in a gravitational dance at the nebula's heart. As one star sheds its outer layers, the other shapes the escaping material into twin cones of dust and gas, viewed edge-on from Earth. The result, that iconic X-shape and the nested rectangles that give the nebula its name. But here's the twist: binary stars aren't rare, yet nowhere else in the known universe do they produce such crisp, angular outflows. It's as if nature decided to break its own rules just this once, crafting a structure that seems almost engineered. The red rectangle's eerie beauty has fueled wild speculation. Its precise symmetry and vivid red glow, caused by rare carbon-based molecules called polycyclic aromatic hydrocarbons, led some to wonder if it might be an alien signal, a cosmic beacon, or even a relic of some long-vanished civilization. Scientists, of course, dismiss this as fantasy, but even they admit the nebula challenges our understanding of how stellar winds and magnetic fields sculpt space. Perhaps most intriguing is the nebula's fleeting nature. The central stars are nearing the end of their lives, and in a few thousand years, a blink in cosmic time, their delicate creation will vanish, dispersing into the interstellar void. The red rectangle, then, isn't just a marvel. It's a temporary exhibit in the grand gallery of the universe, reminding us that even the most extraordinary phenomena are as transient as they are beautiful. And with that, we're primed to explore another cosmic oddity, one where galaxies don't just collide, but devour each other in a slow-motion feast. While the Red Rectangle Nebula dazzles with its fleeting beauty, the cosmos holds darker, more violent spectacles. none more ominous than the cannibalistic tendencies of our closest galactic neighbor, Andromeda. At 2.5 million light-years away, this spiral giant isn't just drifting through space, it's devouring smaller galaxies in a slow-motion feast that might one day include our own Milky Way. Andromeda's hunger isn't new. Astronomers have traced its predatory path through the faint stellar stream's ghostly trails of stars that wrap around it like cosmic spaghetti. These are the remnants of dwarf galaxies torn apart by Andromeda's gravity, their stars assimilated into its sprawling disk. One victim, a dwarf galaxy called M32, orbits Andromeda like a surviving trophy, its core oddly dense, likely all that remains after its outer layers were stripped away. Another, the Triangulum galaxy, may someday meet the same fate, already showing signs of distortion from Andromeda's relentless pull. What makes Andromeda such an efficient predator? Size and gravity. With nearly twice as many stars as the Milky Way, its gravitational influence is immense. But there's a twist. Andromeda isn't just consuming galaxies, it's also changing because of them. Each merger injects fresh gas and stars, altering its structure and even triggering bursts of new star formation. This galactic recycling raises a chilling question: could the Milky Way suffer the same fate? The answer lies in the inevitable dance between our two galaxies. In about 4.5 billion years, the Milky Way and Andromeda will collide, drawn together by gravity in a merger that will reshape both. Simulations show the two spirals tangling, their stars flung into chaotic orbits as they merge into a single, elliptical galaxy nicknamed Milkdromeda. While stars are so far apart that direct collisions are unlikely, the cosmic turmoil will fling some into intergalactic space and ignite furious waves of new star birth. Yet this apocalyptic scenario isn't unique. Galaxy cannibalism is a universal rite of passage. Larger galaxies grow by consuming smaller ones, a process that sculpted the universe since its earliest epochs. Andromeda's violent history, then, isn't just a curiosity, it's a preview of our own galaxy's distant future. A reminder that in the cosmos, even the grandest structures are fleeting, their fates written in the relentless pull of gravity. And as we ponder the devouring nature of galaxies, another mystery looms, one where entire planets, untethered to any star, wander the cosmos in perpetual darkness. Shifting our gaze from the cannibal galaxies devouring their neighbors, let's turn to a world so extravagant it could belong in a billionaire's fantasy, a planet literally glittering with diamonds. Meet 55 Cancri, a super-Earth orbiting so close to its star that its surface is a scorching 2,700 degrees Celsius, hot enough to vaporize metals, yet potentially studded with unimaginable riches. Discovered in 2004, this planet is twice Earth's size but 8 times heavier, a density that initially baffled astronomers. The answer: a carbon-rich composition with up to a third of its mass possibly locked in crystalline forms, diamonds and graphite. Imagine a world where mountains aren't made of rock but of diamond, where rivers of lava cut through valleys of glittering carbon. Scientists speculate that under its searing heat and crushing atmospheric pressure, carbon atoms could have bonded into vast diamond lattices, creating a crust more valuable than any treasure hoard on Earth. But how did this cosmic jewel form? 55 Cancri orbits a star unusually rich in carbon, a stellar quirk that likely influenced the planet's composition. In carbon-heavy systems, planets may form from carbon compounds instead of silicates, birthing worlds where graphite and diamond dominate over granite and basalt. Some theories suggest the planet's interior could even harbor a liquid diamond layer, behaving like a metallic fluid due to extreme pressure, a surreal state of matter impossible on Earth. Yet this diamond paradise is anything but hospitable. Its tight orbit means one side perpetually faces its star, locked in blistering daylight, while the other drowns in eternal night. The temperature difference could generate supersonic winds, scouring the surface with diamond dust storms. Even if you could withstand the heat, the planet's gravity, 3 times Earth's, would pin you down like a bug on a windshield. The discovery of 55 Cancri E challenges our assumptions about planetary diversity. While Earth's geology revolves around silicon and oxygen, this world proves that carbon, the backbone of life here, can sculpt entire planets into landscapes of extreme luxury and violence. It's a reminder that the universe doesn't just host worlds that mirror ours, but ones that defy imagination. And as we marvel at this gem of the cosmos, another enigma calls, a void so vast and empty it seems to defy the very fabric of the universe. But the universe doesn't just dazzle us with diamond planets, it also taunts us with puzzles that unravel the very laws of physics. Enter the black hole information paradox, a cosmic head-scratcher that pits Einstein's relativity against quantum mechanics in a battle science still hasn't resolved. At the heart of this mystery lies a simple question. When something falls into a black hole, does the information about it disappear forever? Stephen Hawking first spotlighted this problem in the 1970s, showing that black holes aren't the eternal traps we once thought. They evaporate over time, emitting what we now call Hawking radiation. But here's the catch: that radiation appears totally random, carrying no trace of the objects the black holes swallowed. If that's true, it violates a core rule of quantum mechanics: information can't be destroyed. It might change form, but it can't vanish without a trace. Imagine burning a book and the ashes revealing nothing about its pages. That's the scale of this paradox. Why does this matter? Because quantum mechanics underpins everything from the atoms in your body to the behavior of stars. If information truly vanishes in black holes, it means our understanding of reality is fundamentally flawed. Some physicists, like Hawking himself, initially argued that information does disappear, sparking decades of debate. Others, like Leonard Susskind, fought back, insisting there has to be a way information escapes, even from a black hole's grip. One leading solution: the holographic principle. It suggests that all the information sucked into a black hole isn't lost, it's smeared across its event horizon like a cosmic fingerprint, encoded in ways we don't yet fully understand. Think of it like a scrambled hard drive. The data's still there, just unreadable without the right decoder. Another wild idea is that black holes might spawn alternate universes, with the information leaking into a new reality. Yet after 50 years, nobody's cracked the case. Even Hawking eventually conceded that information probably escapes, but how remains one of physics' greatest enigmas. It's a reminder that the universe's most extreme places don't just bend space and time, they bend the rules themselves. And as we wrestle with the secrets of black holes, another cosmic oddity waits, a void so eerily empty, it seems to defy the universe's love of clutter. Now let's turn our attention from the depths of black holes to something much closer to home, our own moon. You'd think after decades of study, we'd have all its secrets figured out. But here's the twist: lunar rocks tell a story that doesn't quite add up. These ancient stones, brought back by Apollo missions, are magnetized as if they were once bathed in a strong magnetic field. Yet today, the moon has no global magnetic field to speak of. So what gives? How could a world with no active dynamo, no churning molten core like Earth's, have once generated a magnetic force powerful enough to leave its mark on rocks billions of years old? This mystery starts with the moon's formation. Most scientists agree it was born from a cataclysmic collision between Earth and a Mars-sized object around 4.5 billion years ago. The debris from that impact eventually coalesced into our moon. Early in its life, the moon was molten, and like Earth, it might have had a molten metal core capable of generating a magnetic field through what's called a dynamo effect. But here's the catch: dynamos require sustained heat and movement. Earth's core stays hot thanks to radioactive decay and the slow cooling of our planet's interior. The moon, being much smaller, should have cooled rapidly, shutting down any dynamo within its first billion years. Yet the rocks tell us its magnetic field persisted far longer, perhaps up to 2 billion years. That timeline just doesn't fit, so what kept the moon's magnetic field alive? One theory points to massive impacts. Imagine asteroid collisions so violent they stirred the moon's core, reigniting its dynamo temporarily. Another idea suggests tidal forces from Earth stretching and squeezing the moon's interior like putty, generating heat through friction. There's even a wilder proposal that the moon's crust could have acted like a giant magnetic battery, storing energy from the solar wind and releasing it in pulses. But none of these fully explain the strength or duration of the magnetism we see. Then there's the puzzle of why the field vanished. If impacts or tides powered it, why didn't it flicker back on during later collisions? Some researchers argue the moon's core might have crystallized unevenly, creating short-lived magnetic zones rather than a global field. Others think the rocks themselves might be playing tricks on us, their magnetism possibly altered by shockwaves from meteor strikes long after they formed. What's clear is that the moon's magnetic past is anything but settled. Every explanation has holes, and until we gather more samples, especially from the moon's far side, which we've barely explored, this mystery will linger. It's a reminder that even our nearest cosmic neighbor holds secrets that defy easy answers. And speaking of cosmic enigmas, our next stop takes us to a structure so vast, it stretches the very definition of what we thought possible in the universe. Just when you thought the universe couldn't surprise us any further, we stumble upon a structure so immense, it challenges everything we thought we knew about cosmic scales. Meet the Hercules-Corona Borealis Great Wall, a galactic filament so vast it stretches an almost incomprehensible 10 billion light-years across. To put that into perspective, the observable universe itself is only about 93 billion light-years wide. This means the Great Wall spans more than 1/10 of the entire cosmos we can see. It's not just big, it's cosmically defiant, breaking theoretical limits on how large structures in the universe should be. The discovery of this behemoth came in 2013 when astronomers mapping gamma-ray bursts, the most energetic explosions in the universe, noticed an unusual clustering. These bursts acted like cosmic breadcrumbs, tracing the outline of something far larger than anyone expected. What they revealed was a sprawling network of galaxies, galaxy clusters, and dark matter, woven together in a filament that dwarfs even the Sloan Great Wall, once considered the largest known structure. The Hercules-Corona Borealis Great Wall isn't just a random clump of matter. It's a carefully arranged cosmic highway with galaxies strung along its length like pearls on a necklace, held together by gravity's invisible threads. Here's where things get puzzling. According to the cosmological principle, a cornerstone of modern astronomy, the universe should look roughly the same in all directions on large scales. Matter should be evenly distributed with no single structure dominating. Yet the Great Wall defies this. Its sheer size suggests a level of organization that shouldn't exist under our current models. Some theories propose it's a remnant of primordial density fluctuations, ripples from the Big Bang that somehow avoided being smoothed out over time. Others speculate it could be the result of multiple smaller structures aligning by chance, though the odds of that are astronomically low. Even more intriguing is what the Great Wall implies about the universe's architecture. If structures this colossal can exist, what does that mean for the cosmic web, the vast network of filaments and voids that make up the universe's large-scale structure? Could there be even larger walls hidden in the depths of space, waiting to be discovered? Or is this a rare anomaly, a cosmic Everest that stands alone? For now, the Hercules-Corona Borealis Great Wall remains one of the most tantalizing mysteries in cosmology. It's a reminder that the universe still holds colossal secrets, structures so immense they force us to rethink the very rules we've written about its behavior. And as we continue to map the cosmos with ever more powerful tools, who knows what other giants might be lurking in the darkness? Now, shifting our gaze to another cosmic oddity, let's unravel the mystery of the Eridanus supervoid. Picture the universe as a tapestry of light and shadow, and right in the middle of that tapestry, there's an eerie cold spot, an anomaly in the cosmic microwave background, the faint afterglow of the Big Bang. This spot is far colder than it should be, as if a piece of the universe's warmth has simply gone missing. Astronomers traced this cold spot to the Eridanus constellation, where they discovered something even more baffling, a vast, nearly empty region of space stretching over 1.8 billion light-years across. This supervoid is so enormous that if you were to stand at one edge, you wouldn't just see emptiness, you'd feel the unsettling scale of absence itself. But here's the catch: voids aren't unusual in the cosmos. The universe is full of them, pockets where galaxies are sparse. What makes the Eridanus supervoid special is its sheer size. According to our current understanding of cosmic structure, voids this big should be vanishingly rare. Yet there it is, defying expectations. The leading theory suggests that this supervoid might explain the cold spot in the cosmic microwave background. As light travels through voids, it loses energy, a phenomenon known as the integrated Sachs-Wolfe effect. The idea is that photons from the early universe passing through this immense empty region would lose a tiny bit of energy, making that part of the sky appear colder. But the math doesn't quite add up. Even with its staggering size, the Eridanus supervoid shouldn't cause a temperature drop this severe. Some scientists argue that the cold spot might instead be evidence of a cosmic defect, a flaw in the fabric of spacetime left over from the universe's birth. Others speculate it could hint at something even stranger, like a collision with another universe. What makes this supervoid so tantalizing is the way it challenges our understanding of cosmic probability. Structures in the universe form through a delicate interplay of gravity and dark energy, leading to a predictable distribution of clusters and voids. But the Eridanus supervoid is an outlier, a statistical anomaly that shouldn't exist under our current models. Could it be a fluke, a 1 in a billion chance? Or is it pointing to deeper gaps in our knowledge, perhaps hidden physics governing the universe's expansion we haven't yet discovered? For now, the Eridanus supervoid remains one of the most puzzling enigmas in cosmology. It's a cosmic question mark, urging us to keep looking, keep questioning, and stay humble in the face of the universe's vast and mysterious design. And as we peer deeper into these anomalies, who knows what other secrets might emerge from the darkness? Now let's venture into a phenomenon that sounds like it's straight out of science fiction, the galactic barrier. If you're a fan of Star Trek, you might recognize this term from the show, where it's depicted as an energy field preventing starships from leaving the Milky Way. But here's the twist: our real-life galaxy might have its own version of this cosmic blockade. Scientists have discovered that the Milky Way is surrounded by a vast, invisible halo of high-energy particles. Think of it as a protective bubble, but one that could pose serious challenges for anything trying to travel beyond our galaxy. This barrier isn't made of solid walls or force fields, of course. Instead, it's a turbulent zone of cosmic rays and magnetic fields, stretching tens of thousands of light-years above and below the galactic disk. What makes this barrier so fascinating is its intensity. The particles here are energized to extreme levels, far beyond what we see in the quieter regions of interstellar space. Some theories suggest this might be the result of supermassive black holes at the galaxy's core, spewing out jets of high-energy particles that travel outward and get trapped in the halo. Others propose that it's the cumulative effect of countless supernovae over billions of years, their shock waves pumping energy into the galactic outskirts. The real kicker: this barrier might actually be preventing extragalactic particles from entering the Milky Way with ease. Cosmic rays from distant galaxies, which should theoretically flood our space, seem to be filtered or deflected by this invisible shield. It's almost as if our galaxy has built its own cosmic moat, keeping out some of the universe's most energetic particles. But here's the puzzle. If this barrier is so effective at blocking external particles, could it also hinder future attempts at interstellar or even intergalactic travel? The energy levels here are so extreme that any spacecraft passing through would likely face intense radiation, potentially damaging electronics and endangering human crews. Some researchers speculate that this could be one of the reasons we haven't detected signs of advanced extraterrestrial civilizations. Perhaps they too are confined by similar barriers in their own galaxies. This phenomenon raises deeper questions about our place in the cosmos. Are galaxies like islands, each with their own isolating boundaries, or could there be pathways, cosmic bridges, that allow travel despite these obstacles? For now, the galactic barrier remains one of the Milky Way's most intriguing mysteries, a reminder that even our home galaxy still holds secrets waiting to be uncovered. And as we push the boundaries of exploration, who knows what other cosmic frontiers we might find lurking just beyond our reach? Now, let's dive into something even more mind-bending, a cosmic mystery that challenges our understanding of the universe itself. Picture this: galaxies not just drifting randomly, but being pulled en masse towards something we can't even see. Scientists call it the dark flow, and it's as eerie as it sounds. Back in 2008, astronomers studying the motion of galaxy clusters made a startling discovery. These massive structures weren't just moving apart due to the universe's expansion, they were also being tugged in the same direction, as if drawn by an invisible force. What's baffling is that this motion can't be explained by the gravitational pull of anything within the observable universe. The source of this pull lies beyond the cosmic horizon, in regions we'll never be able to see. So, what could possibly be out there? One leading theory suggests the dark flow might be the gravitational influence of another universe, yes, another universe bumping up against our own in the vast multiverse. Imagine two soap bubbles in a sink gently pressing against each other. The gravity from the other bubble, or in this case, universe, could be warping the motion of galaxies on our side. It's a wild idea, but the data seems to support it. Another possibility is that the dark flow is the remnant of a violent event in the early cosmos, like a colossal collision of space-time that sent ripples through the fabric of reality. Some researchers speculate that this could trace back to the inflationary period right after the Big Bang, when the universe expanded faster than light itself. If pockets of space-time were stretched unevenly, they might have left behind gravitational imprints that still tug on galaxies today. But here's the catch. The dark flow contradicts one of cosmology's foundational principles, the idea that the universe should look roughly the same in all directions on large scales. This motion, concentrated in a specific direction, throws a wrench into that assumption. Skeptics argue it could be a statistical fluke or an artifact of incomplete data. Yet, multiple independent studies have detected the same peculiar motion, making it harder to dismiss. What does this mean for our understanding of reality? If the dark flow is real, it hints at a cosmos far stranger than we've imagined, one where unseen forces or even other universes shape our fate. It's a humbling reminder that, for all our advances, the universe still holds cards it hasn't shown us. And as we peer deeper into the void, who knows what other hidden currents might be guiding the cosmic dance? Now, let's turn our attention to a celestial oddity that looks like it was plucked straight from a sci-fi novel. Meet Hoag's object, a galaxy so peculiar that when astronomer Arthur Hoag stumbled upon it in 1950, he initially thought it might be a trick of the light. What makes this galaxy so extraordinary? Imagine a perfect ring of stars glowing blue with youthful energy, encircling a golden core of older stars like a cosmic bullseye floating in the void. Even more baffling, there's no visible bridge of stars or gas connecting the ring to the core, defying everything we know about how galaxies typically form. Most galaxies, like our Milky Way, have spiral arms or chaotic elliptical shapes, molded by gravity and collisions over billions of years. But Hoag's object, It's a pristine circle, nearly symmetrical, as if someone sculpted it with celestial precision. The ring itself spans about 120,000 light-years larger than our entire galaxy, and sparkles with clusters of hot, newborn stars, while the core is packed with cooler, ancient stars. This stark contrast suggests two distinct eras of star formation, but how they ended up in this configuration is still a mystery. One leading theory is that Hoag's object is the aftermath of a galactic collision, where a smaller galaxy punched through the center of a larger one billions of years ago. The impact could have sent ripples through the gas and dust, triggering star formation in a ring-like shockwave around the surviving core. It's a cosmic ripple effect frozen in time. But here's the puzzle. There's no sign of the intruder galaxy, no debris trail, no telltale distortions, just this eerily perfect ring. Another idea is that Hoag's object represents an extreme version of a barred galaxy, where a central bar of stars funnels material outward, creating rings. But again, the flawless symmetry and lack of connecting material make this explanation feel incomplete. Even more intriguing, astronomers have spotted a second, fainter ring of stars farther out, an outer halo that hints at an even more complex history. What truly sets Hoag's object apart is its isolation. Most ring galaxies are found in dense clusters shaped by interactions with neighbors, but Hoag's object floats alone, a cosmic hermit, making its formation even harder to explain. Some researchers speculate it could be a rare example of a pure ring galaxy, formed under conditions we've yet to understand. This celestial enigma challenges our assumptions about galactic evolution, proving that the universe still has templates we've never seen before. And while Hoag's object might not have the flashy drama of black holes or dark matter, its quiet perfection reminds us that sometimes the most profound mysteries are the ones that look deceptively simple. Up next, we'll explore stars that defy death itself, zombie stars that rise from the ashes of their own destruction. Now, let's shift our gaze to one of the cosmos' most bizarre survivors, stars that refuse to die, even after facing annihilation. These are the zombie stars, celestial phoenixes that somehow cheat death after their explosive demise in a supernova. And no, this isn't science fiction. Imagine a star torn apart in one of the universe's most violent events, only to emerge from the wreckage, forever altered but still burning. Take Tycho's supernova remnant, named after the famed astronomer Tycho Brahe, who witnessed its explosion in 1572. For centuries, astronomers studied the expanding debris cloud, assuming the original star was completely obliterated. But in 2004, they found something shocking: a surviving companion star flung away from the blast at an incredible speed. This star wasn't just a bystander, it was likely the trigger for the supernova itself. Here's how it happened. Tycho's supernova was a type Ia, a thermonuclear detonation that occurs when a white dwarf, the dense core of a dead star, steals too much material from a neighboring star. The runaway fusion reaction should annihilate both stars. Yet, against all odds, the companion star endured, battered but intact, like a ship surviving a tsunami. How does a star survive such cataclysm? The answer lies in the dynamics of stellar theft. In binary systems where one star is a white dwarf, the dwarf's gravity can siphon gas from its partner. If it pulls too much, it crosses a critical mass limit and explodes. But the companion, though stripped of its outer layers, might retain enough mass to stay bound together. Simulations suggest these stars are left bruised, scorched by the blast, missing chunks of their atmosphere, and hurtling through space at speeds up to several hundred kilometers per second. Zombie stars aren't just cosmic curiosities, they are forensic clues. Their scars tell us exactly how type Ia supernova unfold, events so uniform in brightness that astronomers use them as standard candles to measure cosmic distances. Without understanding the role of surviving companions, our measurements of the universe's expansion, including dark energy's influence, could be flawed. But Tycho's companion isn't alone. In 2014, astronomers found another potential zombie star near supernova remnant 326 in the Large Magellanic Cloud. Unlike Tycho's hyperactive survivor, this one moved sluggishly, hinting at a different kind of stellar relationship before the explosion. Each discovery peels back another layer of mystery, revealing that supernovae aren't always the end. Sometimes they're a rebirth. Next, we'll turn to a star so ancient it seems to defy time itself, a celestial Methuselah whose very existence challenges our understanding of the cosmos. Switching focus to another cosmic enigma, let's unravel the story of a star that seems to defy time, HD 140283, better known as the Methuselah star. This ancient celestial body has astronomers scratching their heads because at first glance it appears older than the universe itself. Yes, you heard that right. A star that might have existed before the cosmos as we know it even began. Discovered over a century ago, the Methuselah star lies just 190 light-years away in the constellation Libra. What makes it so baffling? Initial estimates pegged its age at around 16 billion years, but here's the problem. The universe is only 13.8 billion years old. A star cannot logically predate the space it inhabits, so how did science reconcile this glaring contradiction? The key lies in the way we measure stellar ages. Astronomers determine a star's age by analyzing its composition, particularly the amount of oxygen and iron it contains. Older stars, born before heavier elements were common, have very little metal content. Methuselah is a metal-poor subgiant which initially suggested extreme antiquity, but early calculations didn't account for all the variables. Revised studies using data from the Hubble Space Telescope fine-tuned the measurement. By factoring in the star's distance, brightness, and nuclear fusion processes, astronomers adjusted its age to 14.5 billion years, still ancient, but now with a crucial margin of error that places it within the universe's timeline. The discrepancy arises from uncertainties in stellar physics, like convection rates in its core and the opacity of its outer layers. But the Methuselah star's paradox doesn't end there. Its motion reveals another clue. It's speeding through the Milky Way at over 1 million miles per hour, far faster than most stars in our galactic neighborhood. This suggests it wasn't born here but was likely hurled into our region during a chaotic gravitational encounter, possibly with a long-vanished dwarf galaxy. Why does this matter? Because stars like Methuselah are rare time capsules, preserving conditions from the universe's infancy. Studying them helps us test cosmic age estimates and refine our understanding of the Big Bang's aftermath. Some theories even propose that tweaks to dark energy's behavior or early expansion rates could explain how such old stars exist without breaking cosmology's rules. The Methuselah star reminds us that the universe still holds surprises and that even our best measurements are works in progress. Next, we'll turn our attention to another shadowy mystery lurking at the edge of our solar system. The hunt for a hidden giant, the elusive planet 9. Now, let's venture into the frigid outskirts of our solar system, where an unseen giant might be lurking in the darkness, the enigmatic planet 9. For decades, astronomers have scrutinized the orbits of distant icy bodies in the Kuiper belt, only to find peculiar patterns that hint at the gravitational pull of something massive and hidden. The story begins with a group of small, icy objects beyond Neptune. These Kuiper belt inhabitants don't move as expected. Instead of scattered, randomized orbits, many cluster together in elongated paths that tilt at odd angles. This bizarre alignment suggests the influence of a far larger object, one roughly 10 times the mass of Earth, quietly shaping their trajectories from the shadows. Why hasn't Planet 9 been spotted yet? The answer lies in its distance. If it exists, this world could orbit up to 20 times farther from the Sun than Neptune, making it incredibly faint and slow-moving. A single trip around the Sun might take 10,000 to 20,000 years, leaving just a tiny, elusive dot in our telescopes. the hunt for Planet 9 has sparked some of the most creative detective work in modern astronomy. Researchers have used mathematical models to narrow down its possible location, simulating how its gravity would sculpt the orbits of nearby objects. Some even combed through old survey data, hoping to spot its faint glow hidden in archival images, but the mystery deepens. If Planet 9 is real, how did it get there? One theory suggests it was ejected during the solar system's chaotic infancy, slingshot outward by gravitational tugs from Jupiter or Saturn. Another proposes it might be a rogue planet captured from another star system long ago. The implications are staggering. Discovering Planet 9 wouldn't just add a new world to our solar system's roster, it would rewrite our understanding of how planetary systems form and evolve. Until then, the search continues, a tantalizing reminder that even in our own cosmic backyard, secrets still wait to be uncovered. Next, we'll explore a more violent cosmic drama, the Milky Way's relentless devouring of its neighbor, the Sagittarius dwarf galaxy. Now, let's shift our gaze to a cosmic spectacle unfolding right in our galactic backyard, a slow-motion collision of epic proportions. The Milky Way isn't just a serene spiral of stars, it's a predator, and its latest victim is the Sagittarius dwarf galaxy. This tiny neighbor, barely 1/10,000th the mass of our galaxy, is being ripped apart strand by strand, its stars scattered like crumbs in a gravitational tide. The saga began billions of years ago when the Sagittarius dwarf, a satellite galaxy orbiting the Milky Way, ventured too close. Like a spider caught in a web, it couldn't escape the pull of our galaxy's immense gravity. Over time, the dwarf galaxy made multiple passes around the Milky Way, and with each orbit, tidal forces stretched and shredded it further. Today, astronomers can trace its remnants, streams of stars arcing across the sky, a ghostly signature of its destruction. What makes this carnage so fascinating is the forensic evidence it leaves behind. The Sagittarius stream, a ribbon of stars torn from the dwarf galaxy, wraps around the Milky Way like a cosmic smoke ring. By mapping these stellar debris, scientists have reconstructed the dwarf's doomed orbit and even estimated when each bite was taken. The Milky Way isn't just swallowing Sagittarius whole, it's feasting in cycles, with clumps of stars being stripped away every few 100 million years. But there's a twist. This isn't just a one-sided tragedy. The Sagittarius dwarf's death throes are reshaping the Milky Way too. As its stars are absorbed, they stir up our galaxy's disk, creating ripples in its structure. Some researchers believe these mergers could explain oddities in the Milky Way's outer halo, where stars move in unexpected ways. It's a reminder that even the victim can leave its mark on the predator. The fate of the Sagittarius dwarf holds clues to a broader cosmic truth. Galaxies grow by consuming others. The Milky Way itself likely formed from countless mergers, and Andromeda, our nearest galactic rival, is on a collision course with us billions of years from now. In the grand timeline of the universe, even destruction fuels creation. As we peer deeper into this celestial drama, another mystery beckons, one that echoes the silence of the cosmos itself. Why, after decades of listening, have we heard nothing from intelligent life beyond Earth? The answer may lie in the haunting enigma known as the Great Silence. But let's pause for a moment and consider a puzzle closer to home, or rather, the eerie absence of puzzles where we expected them. After decades of scanning the skies with radio telescopes, listening for even the faintest whisper of intelligent life, the universe has responded with silence. No signals, no patterns, just the endless static of cosmic noise. This is the Great Silence, a mystery that has left scientists both baffled and humbled. The search for extraterrestrial intelligence, or SETI, began in earnest in the 1960s, fueled by optimism and the belief that advanced civilizations must be out there. With billions of stars in our galaxy alone, many hosting planets in the so-called habitable zone, the odds seemed in our favor. Yet here we are, half a century later, with nothing but static. Not a single confirmed message, not even a suspicious blip. So where is everybody? One possibility is that we're simply not listening correctly. Imagine trying to tune into a radio station without knowing the frequency. It's a needle in a haystack problem. Alien civilizations might be using communication methods we haven't even imagined, like neutrino beams or quantum entanglement, leaving our radio telescopes deaf to their calls. Or perhaps their signals are too faint, drowned out by the cosmic background noise before they ever reach us. Then there's the darker explanation, the Great Filter. This theory suggests that at some point in a civilization's evolution, whether before they develop interstellar communication or after, something catastrophic wipes them out. It could be nuclear war, runaway AI, ecological collapse, or a disaster we haven't even conceived. If the filter lies ahead of us, humanity's future might be far bleaker than we'd like to admit. But let's not lose hope just yet. The universe is vast and our search has barely scratched the surface. We've only examined a tiny fraction of stars and for relatively short periods. Advanced civilizations might be rare, or they might be deliberately avoiding contact, adhering to some cosmic version of the Prime Directive. There's also the chance they're already here, observing us in ways we can't detect, a notion that's equal parts thrilling and unsettling. As we grapple with the Great Silence, it's worth remembering how young we are in the cosmic timeline. Intelligent life might be a fleeting phenomenon, rising and vanishing before others can notice. Or perhaps we're the first, destined to be the ancient civilization future species will one day search for. Whatever the answer, the silence isn't just a lack of noise, it's a mirror, reflecting back our own place in the universe's grand, unknowable story. And speaking of reflections, our next cosmic oddity turns the mirror on itself quite literally. Prepare to encounter Hoag's object, a galaxy so perfectly ringed it looks like it was drawn by a celestial architect. Now, let's unravel one of the most breathtaking blueprints of the cosmos, a structure so vast it connects everything in the universe, yet remains invisible to the naked eye. Picture the universe not as a random scatter of galaxies, but as an intricate, glowing spiderweb stretched across the void. This is the cosmic web, the universe's hidden skeleton, and it holds the answer to how everything from the tiniest galaxy to the largest superclusters fits together. At its heart, the cosmic web is a network of nearly unfathomable scale. Imagine threads of galaxies, gas, and dark matter weaving through space, forming filaments that stretch hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters swarm like glittering metropolises, while between them lie vast, eerie voids, regions so empty they'd take 100 million years to cross at light speed. If you could see it all, the universe would look less like a starry night and more like a labyrinth of light and shadow. But how did this structure emerge? The story begins with dark matter, the invisible glue that binds the cosmos. After the Big Bang, tiny fluctuations in density created gravitational wells where dark matter pooled, pulling ordinary matter, hydrogen, helium, and eventually galaxies into its grasp. Over billions of years, these patches grew into filaments with galaxies strung along them like pearls on a string. The voids, meanwhile, are the leftover deserts, regions where gravity lost the tug of war. What's truly mind-bending is how recent this discovery is. For centuries, astronomers saw the universe as a haphazard collection of stars and nebulae. It wasn't until the late 20th century, with advanced telescopes and computer simulations, that we glimpsed the web's grand design. Maps like the Sloan Digital Sky Survey revealed its patterns, while simulations like the Millennium Run showed how dark matter's gravitational choreography shaped everything. Yet mysteries remain. Why do some filaments appear denser than others? Could there be unknown forces at play, sculpting the web in ways we don't yet understand? And what lurks in those voids? Are they truly empty or hiding something stranger? The cosmic web isn't just a map of the universe, it's a puzzle box, each filament a clue to the cosmos's deepest secrets. As we marvel at this celestial tapestry, our next cosmic wonder takes us to an object so perfectly symmetrical, it defies belief. Get ready to meet Hoag's object, a ringed galaxy that looks less like a natural formation and more like a portal to another realm. Now, shifting our gaze to something both hauntingly beautiful and scientifically puzzling, let's explore the Phantom Galaxy, officially known as Messier 74. This cosmic enigma lies 32 million light-years away in the constellation Pisces, and it's a masterpiece of symmetry. Unlike the chaotic swirls of many galaxies, M74 boasts near-perfect spiral arms, so pristine they look almost engineered. But here's the twist: despite its striking appearance, this galaxy is eerily faint, earning its ghostly nickname. What makes the Phantom Galaxy so dim? The answer lies in its composition. M74 is what astronomers call a grand design spiral, a rare breed of galaxy where the arms wind outward with mathematical precision. But unlike brighter spirals like the Milky Way or Andromeda, it lacks dense star-forming regions along its arms. Instead, its luminosity comes from a delicate balance of older stars and diffuse gas, giving it a soft, almost ethereal glow. To spot it, you'd need a powerful telescope. It's like trying to see a whisper in a crowded room. Yet, its faintness isn't the only mystery. The Phantom Galaxy's core holds a supermassive black hole, just like many others, but here's the catch: it's unusually quiet. Most galaxies with active black holes blast out radiation as they devour nearby matter, but M74's heart is strangely subdued. Some scientists speculate that it might be in a dormant phase, or perhaps its feeding process is inefficient, leaving more questions than answers. Adding to the intrigue, M74 is a hotspot for supernova, stellar explosions that briefly outshine entire galaxies. In just the past few decades, astronomers have observed 3 in its spiral arms. These violent events hint at pockets of hidden activity, suggesting that despite its calm appearance, the Phantom Galaxy has moments of dramatic flair. What can this ghostly spiral teach us? For one, it challenges our assumptions about how galaxies evolve. Its perfect structure implies a stable, undisturbed life, yet its faintness and sporadic explosions suggest a more complex story. Could it be a cosmic fossil preserving conditions from an earlier era? Or is it quietly evolving in ways we don't yet understand? As we ponder these questions, our journey through the cosmos takes another unexpected turn. Ahead lies a phenomenon that defies the very notion of a galaxy's boundaries, a place where stars break free from gravity's grip and hurtle into the void at unimaginable speeds. Stay with us as we uncover the secrets of hypervelocity stars, the universe's runaway rebels. But before we chase after runaway stars, let's take a detour into the shadowy realm of rogue planets, worlds without suns, drifting through the cosmos like cosmic nomads. Imagine a planet untethered from any star, sailing through the void in eternal night. These aren't science fiction. They're real, and they defy everything we thought we knew about how planets form. Rogue planets, sometimes called orphan planets or free-floating planets, are celestial rebels that don't orbit a star. Instead, they wander the galaxy alone, unlit and untethered. How do they exist? There are 2 leading theories. Some may form like regular planets, born from the swirling gas and dust around a young star, only to be violently ejected by gravitational tugs from sibling planets or passing stars. Others might collapse directly from gas clouds too small to ignite into failed stars that never quite made the cut. Detecting these dark wanderers is a monumental challenge. Without a host star's light to reflect, they're nearly invisible. But astronomers have tricks. Sometimes a rogue planet's gravity bends the light of distant stars behind it, a phenomenon called microlensing. Other times, we spot their faint infrared glow, the residual heat left over from their formation, slowly bleeding into space. The numbers are staggering. Estimates suggest there could be billions of rogue planets in our galaxy alone, possibly outnumbering stars. Some might even be Earth-sized, with conditions eerily similar to our own world, except for one glaring absence: a sun. Picture a frozen, airless landscape where the only light comes from distant stars, too faint to cast shadows. Yet there's a twist. Some rogue planets could harbor thick atmospheres trapping heat, or even subterranean oceans warmed by radioactive decay or tidal forces from ancient moons. In theory, these dark worlds might host life, surviving in pockets of warmth beneath icy shells. One of the most fascinating discoveries is a rogue planet roughly the size of Jupiter, drifting just 20 light-years away. It's young enough to still glow from its formation, offering a rare glimpse into these solitary worlds. But the real shocker: some rogue planets may not be entirely dark. A few could have moons with active geology, like Jupiter's volcanic Io, creating fleeting sources of light in the endless black. What does their existence mean for us? Rogue planets challenge the very definition of a planet. They force us to rethink how solar systems evolve, and they hint at a universe far more dynamic and chaotic than we imagined. Could one ever wander close to our solar system? It's unlikely, but if it did, its gravity could send comets hurtling toward Earth, or even steal a planet from our sun's grip. As we leave these lonely wanderers behind, our next stop takes us to the opposite extreme: not a world without a star, but a star so dense it defies the laws of physics. Stay with us as we dive into the mind-bending reality of neutron starquakes, where entire stars shudder and crack under impossible pressures. Now, let's shift our gaze from the silent drift of rogue planets to the violent tremors of the universe's most extreme stellar remnants: neutron stars. These cosmic powerhouses are born from the explosive deaths of massive stars, collapsing into spheres so dense that a single teaspoon of their material weighs as much as a mountain. But what happens when these ultra-dense objects suddenly shudder and crack? Enter the bizarre phenomenon of neutron starquakes, where the very fabric of a star's surface fractures under unimaginable pressure. Neutron stars are already extreme by nature, spinning at dizzying speeds, some completing hundreds of rotations every second. But occasionally, astronomers detect a sudden speed up in their rotation, followed by a gradual slowdown. These events are known as glitches, and they're thought to be caused by starquakes. Picture this: the star's rigid outer crust, made of iron nuclei packed into a crystalline lattice, fractures under intense magnetic and gravitational stress. Meanwhile, beneath the crust lies a superfluid ocean of neutrons flowing with zero friction. When the crust cracks, the superfluid's momentum transfers to the star's surface, causing it to spin faster in a cosmic hiccup. One of the most studied examples is the Vela pulsar, a neutron star that glitches roughly every 3 years. Each event releases energy equivalent to a magnitude 23 earthquake trillions of times more powerful than anything Earth could withstand. But here's the twist: despite these cataclysmic ruptures, neutron stars don't fly apart. Their immense gravity, billions of times stronger than Earth's, holds them together even as their surfaces splinter like ice on a frozen lake. What makes these starquakes even stranger is their connection to magnetars, a subclass of neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. In 2004, a magnetar named SGR 1820-20 released a starquake so violent it sent ripples through spacetime itself, a gamma-ray burst detected across the galaxy. For a fraction of a second, it outshone the entire Milky Way. The study of neutron starquakes isn't just about cosmic spectacle. These events offer clues about the behavior of matter under conditions impossible to replicate on Earth. By observing glitches, scientists probe the limits of nuclear physics, testing theories about superfluidity and the nature of ultra-dense matter. Some researchers even speculate that the faint, repeating gravitational waves detected by observatories like LIGO could be linked to persistent starquakes. As we unravel the mysteries of these trembling stellar corpses, we're reminded that the universe is far from silent. From rogue planets adrift in darkness to neutron stars ringing like cosmic bells, each phenomenon pushes the boundaries of our understanding. Up next, we'll confront another cosmic contradiction, the Hubble tension, where the universe's expansion rate refuses to add up, leaving astronomers scratching their heads. Now, let's tackle one of the most pressing mysteries in modern cosmology, the Hubble tension. This isn't just a minor disagreement among scientists. It's a full-blown cosmic puzzle that challenges our very understanding of how the universe expands. Imagine measuring the speed of a car with two different radar guns, only to get wildly different results every time. That's essentially what's happening here, but on a universe-sized scale. For decades, astronomers have relied on two primary methods to measure the expansion rate of the universe, known as the Hubble constant. The first method looks at the cosmic microwave background, the afterglow of the Big Bang, using space telescopes like Planck. This approach gives us a snapshot of the early universe, suggesting an expansion rate of around 67 kilometers per second per megaparsec. But the second method, which studies pulsating stars called Cepheids and exploding supernova in nearby galaxies, paints a different picture, yielding a faster rate of roughly 73 kilometers per second per megaparsec. At first glance, that difference might not seem huge, but in the precise world of cosmology, it's a glaring discrepancy. These methods have been refined over years, and yet the gap stubbornly persists, defying easy explanations. If both measurements are correct, it implies there's something fundamentally wrong with our current models of the universe. Could dark energy be evolving in ways we don't understand? Is there an undiscovered particle influencing expansion? Or is there a flaw in how we interpret the cosmic microwave background? One tantalizing possibility involves early dark energy, a hypothetical form of energy that might have briefly surged in the universe's infancy, altering its expansion history. Another theory suggests that our local region of the universe sits in a peculiar void, distorting measurements. But so far, none of these ideas have fully resolved the tension. The stakes are high because the Hubble constant is the cornerstone of cosmology, tying together the age, size, and fate of the universe. If we can't reconcile these numbers, it could mean rewriting chapters of our cosmic playbook. What makes this debate so thrilling is that it's not just about numbers on a page. It's a reminder that the universe still holds secrets we haven't cracked. Whether the solution lies in new physics, better measurements, or a revolutionary rethink of cosmic history, the Hubble tension keeps astronomers on their toes. And as we push the boundaries of observation with next-generation telescopes, we might finally uncover the missing piece of this puzzle. Up next, we'll turn our attention to another cosmic oddity, a potential moon orbiting a distant exoplanet, a discovery that could reshape how we think about alien worlds. Now, let's journey beyond our solar system to a distant exoplanet where astronomers may have spotted something extraordinary, a moon orbiting another world. This isn't just any moon. If confirmed, Kepler 1625b would be the first exomoon ever discovered, a groundbreaking find that could redefine our understanding of alien planetary systems. The hunt for exomoons has been a daunting challenge. Detecting a planet outside our solar system is hard enough, but spotting a moon around one, that's like trying to see a firefly next to a spotlight from thousands of miles away. Yet, in 2017, astronomers using the Kepler Space Telescope noticed something peculiar about the gas giant Kepler 1625b. As it passed in front of its host star, causing a dip in starlight, there was an additional, smaller dip, a tantalizing hint of a moon trailing behind. Further observations with the Hubble Space Telescope added weight to the claim. The data revealed subtle gravitational tugs on the planet, suggesting the presence of a massive companion. Estimates put this potential moon at roughly the size of Neptune, making it a behemoth compared to anything in our solar system. Imagine a moon so large it could have its own atmosphere, weather systems, or even moons of its own. The very idea stretches our imagination of what's possible in the cosmos, but the discovery hasn't been without controversy. Some researchers argue the data could be explained by stellar activity or instrumental quirks. Others point out that a moon this big challenges current theories of moon formation. Typically, moons are either born from planetary collisions like Earth's moon or captured from surrounding material like many of Jupiter's moons. A Neptune-sized moon defies these models, raising questions about how such a colossal companion could form and remain stable. What makes this search so thrilling is its implications. Moons are crucial to the story of life in our solar system. Europa and Enceladus, with their subsurface oceans, are prime candidates for harboring life. If moons like Kepler 1625b exist, they could vastly expand the number of habitable environments in the galaxy. Even this candidate's extreme size opens doors to bizarre, untested astrophysical processes. As telescopes grow more powerful, the hunt for exomoons will intensify. Whether Kepler 1625b stands the test of time or not, it's a reminder that the universe is full of surprises, and sometimes they're hiding in the shadows of distant worlds. Next, we'll explore a paradox that ties the evolution of life on Earth to the Milky Way's relentless motion through space. Now, let's turn our gaze from distant moons to a mystery much closer to home, one that ties the fate of life on Earth to the grand dance of our galaxy. Every 225 to 250 million years, our solar system completes one orbit around the Milky Way center. This journey isn't a smooth cruise through empty space. Instead, it's a perilous trek through regions teeming with cosmic hazards, dense molecular clouds, deadly radiation, and gravitational chaos. And here's the paradox: despite these recurring dangers, complex life not only survived but thrived. How did Earth avoid annihilation every time it crossed these galactic danger zones? Picture the Milky Way as a vast, spinning disk with spiral arms, regions packed with stars, gas, and dust. As our Sun orbits, it periodically drifts into these arms, where the density of material increases dramatically. Some scientists argue these crossings could trigger catastrophic events, asteroid bombardments from disturbed comets in the Oort cloud, or nearby supernova unleashing gamma-ray bursts powerful enough to strip away Earth's ozone layer. Yet, fossil records show life persisted through these intervals, even during periods of mass extinction. One theory suggests our solar system's position might offer a shield. The Sun's orbit is slightly out of sync with the spiral arms, meaning we might spend less time in the most hazardous zones than previously thought. Another clue lies in Earth's own resilience. Our planet's magnetic field deflects harmful cosmic rays, while its atmosphere absorbs ultraviolet radiation. Plate tectonics and volcanic activity recycle nutrients, fostering biodiversity even after global catastrophes. But the paradox deepens when we consider timing. The last 5 major mass extinctions loosely align with spiral arm crossings, but none wiped out life entirely. Instead, they sparked evolutionary rebounds like the rise of mammals after the dinosaurs' demise. Could these galactic encounters actually accelerate evolution by clearing ecological niches? The enigma grows when we factor in the rare Earth hypothesis, which posits that complex life requires an improbable combination of stable conditions. If true, why didn't galactic hazards reset the clock? Some researchers propose that the Milky Way's galactic habitable zone, a region with just the right mix of heavy elements and fewer cosmic threats, offers a safe harbor. Yet even this zone isn't static. As the galaxy evolves, so do its dangers. What makes this paradox so compelling is its implications for life elsewhere. If Earth's survival was a fluke, the odds of finding complex life in the galaxy drop. But if our planet's endurance reflects a hidden cosmic safety net, the universe might be richer with life than we imagine. As we unlock more secrets of our galactic journey, one thing is certain: the Milky Way isn't just our home. It's an active participant in the story of life itself. Next, we'll revisit one of history's most explosive cosmic mysteries, the Tunguska event, and why it still puzzles scientists over a century later. But before we unravel what really happened over Siberia, let's set the scene. On June 30th, 1908, a blinding fireball streaked across the sky before detonating with the force of a 10 to 15 megaton bomb, nearly 1,000 times more powerful than Hiroshima. The blast flattened 80 million trees across 800 square miles near the Tunguska River, yet left no crater. Witnesses hundreds of miles away reported feeling searing heat, hearing deafening booms, and seeing shockwaves that knocked people off their feet. For decades, the lack of physical evidence fueled wild theories, from antimatter annihilation to a miniature black hole passing through Earth. Today, most scientists agree it was likely a stony asteroid, roughly 160 to 200 feet wide, that exploded 3 to 6 miles above the surface. The angle of entry and intense heat vaporized it entirely, creating a shock wave rather than an impact. But here's where the mystery deepens. No fragments of the object have ever been definitively linked to the event. Expeditions to the region found microscopic silicate and magnetite spheres in the soil, hinting at extraterrestrial origins, but nothing conclusive. Even more puzzling, trees at the epicenter were left standing, stripped of branches, while those farther away were toppled in radial patterns. This suggests multiple explosion waves, something modern models struggle to replicate. Then there's the eerie atmospheric aftermath. For nights after the blast, skies across Europe and Asia glowed so brightly that people could read newspapers outdoors at midnight. Scientists suspect dust from the vaporized asteroid lingered in the upper atmosphere, scattering sunlight. But why did the effect last weeks when similar events like the Chelyabinsk meteor in 2013 caused only brief anomalies? Some researchers propose the Tunguska object's composition was unusual, perhaps rich in volatile materials that dispersed differently. The event's legacy isn't just scientific. It redefined humanity's understanding of cosmic threats. If the asteroid had entered Earth's atmosphere just 4 hours later, it would have obliterated St. Petersburg, killing millions. This near miss spurred early efforts to track near-Earth objects, eventually leading to NASA, a Planetary Defense Coordination Office. Yet Tunguska's biggest lesson might be humility. Over a century later, we still can't fully explain why the explosion left such contradictory clues, or whether it was a fluke or a warning of larger dangers lurking in the cosmos. Now, shifting our gaze from Earth to our enigmatic neighbor, let's untangle the eerie spectacle at Venus's south pole, the Venusian vortex. Unlike any weather phenomenon in our solar system, this swirling double-eyed storm has baffled scientists since its discovery. Imagine a hurricane, but one that doesn't dissipate, doesn't move, and has not one but two centers of rotation locked in a perpetual dance. That's the Venusian vortex, a climatic enigma that defies everything we know about planetary atmospheres. First spotted by the European Space Agency's Venus Express orbiter in 2006, this vortex spans nearly 2,000 miles, wide enough to swallow continents on Earth. It hovers stubbornly over the South Pole, a region already shrouded in mystery due to Venus's thick, toxic clouds. What makes this vortex extraordinary isn't just its size or persistence, but its bizarre structure. Most storms, like Jupiter's Great Red Spot, have a single eye, but the Venusian vortex splits into two distinct rotating cores, sometimes merging, sometimes drifting apart as if guided by invisible hands. Scientists believe the vortex is fueled by Venus's super-rotating atmosphere, where hurricane-speed winds circle the planet every 4 Earth days, despite Venus itself taking 243 days to complete one rotation. This creates colossal atmospheric waves that collide at the poles, forming the vortex. But why two eyes? One theory suggests it's due to instability in these colliding wind patterns, like two whirlpools briefly merging in a bathtub drain. Another proposes that Venus's polar vortices are shaped by giant dipoles, paired high-pressure and low-pressure systems that twist the storm into its eerie double form. Yet the biggest puzzle is the vortex's endurance. Earth's hurricanes die out in days when they hit land or cool waters, but the Venusian vortex has persisted for at least 2 decades, possibly longer. Some researchers speculate that the planet's extreme greenhouse effect, with surface temperatures hot enough to melt lead, acts like a battery, constantly recharging the storm. Others point to Venus's lack of oceans or land masses, leaving nothing to disrupt the atmospheric chaos. What's at stake isn't just understanding Venus. This vortex could hold clues to extreme weather on exoplanets or even Earth's past climate shifts. If we could decode why Venus's atmosphere behaves so violently, we might predict how other worlds or our own respond to atmospheric upheaval. For now, the Venusian vortex remains one of the solar system's most mesmerizing riddles, a reminder that even our closest planetary neighbors guard secrets we've only begun to uncover. Now, let's turn our attention from Venus to its rusty red neighbor, Mars, where another cosmic mystery is unfolding: the enigmatic methane spikes detected in its thin atmosphere. Unlike the swirling vortices of Venus, these fleeting gas plumes on Mars have sparked a heated debate among scientists, with some daring to ask the ultimate question: could this be a sign of life? Methane, a simple organic molecule, is often produced by living organisms here on Earth. Think cows, wetlands, or even microbes deep underground. But on Mars, where no cows graze and no swamps bubble, its presence is far more puzzling. The first whiffs of methane were detected by the European Space Agency's Mars Express orbiter back in 2004. And since then, NASA's Curiosity rover has confirmed sporadic spikes in the gas, sometimes reaching levels 10 times higher than the background concentration. What's bizarre is how suddenly these plumes appear and vanish, sometimes within just a few hours, as if Mars is teasing us with whispers of a hidden secret. So where does this methane come from? Scientists have 2 leading theories, each as tantalizing as the other. The first suggests geological processes like serpentinization, a reaction between water, carbon dioxide, and certain minerals deep underground that can produce methane without any biological help. Mars has plenty of these minerals, and if liquid water still exists beneath its surface, this could explain the gas. The second, far more thrilling possibility is microbial life. Certain extremophile microbes on Earth thrive in harsh, airless environments, like deep underground or in volcanic vents, and they exhale methane as a byproduct. Could similar microbes be lurking beneath Mars's barren surface, quietly releasing these mysterious plumes? The mystery deepens when we consider the methane's erratic behavior. On Earth, methane lingers in the atmosphere for around a decade before breaking down. But on Mars, it disappears within a few hundred days, far faster than sunlight or chemical reactions should allow. Some researchers propose that the gas is being rapidly absorbed by the Martian soil or destroyed by unknown atmospheric chemistry. Others wonder if the methane is being intermittently sealed and released by underground ice or seasonal changes, creating these sudden bursts. NASA Perseverance rover, equipped with a more advanced methane detector, has been scouring Jezero crater for clues. Meanwhile, the European-Russian ExoMars Trace gas orbiter has curiously failed to detect significant methane from orbit, adding another layer of confusion. Could the methane be so localized that only ground-based instruments catch it, or are the orbital measurements missing something? The stakes couldn't be higher. If the methane is biological, it would be the most compelling evidence yet that life exists or once existed beyond Earth. Even if it's geological, it hints at active processes that could sustain future human exploration. For now, Mars keeps its secrets close, but with every new rover and orbiter, we're peeling back another layer of this cosmic whodunit. One thing's certain: the answer, when it comes, will rewrite our understanding of the red planet and perhaps life itself. Next, we'll venture beyond our solar system to confront a paradox that has haunted astronomers for decades: the unsettling silence in our search for extraterrestrial intelligence. Why, in a universe teeming with stars and planets, have we heard nothing? The answer might be more troubling than we think. Now, shifting our gaze from the silent enigmas of Mars to the dazzling spectacle of Saturn, we encounter one of the most striking geometric wonders in our solar system: the Saturn hexagon. This gargantuan, six-sided storm swirling at the planet's north pole defies everything we know about atmospheric physics. Unlike the chaotic cyclones seen on other planets, this hexagon is eerily precise, as if etched by some cosmic hand. First spotted by Voyager in the 1980s, the hexagon spans nearly 20,000 miles across, wide enough to fit two Earths side by side, and its jet stream walls race at speeds of over 200 miles per hour. What's baffling is its stability. While most planetary storms churn and fade within days or weeks, this hexagonal monster has persisted for at least 4 decades, possibly much longer. How does a storm maintain such perfect symmetry for so long in a gas giant's turbulent atmosphere? Scientists have wrestled with this puzzle for years. One leading theory suggests the hexagon is a colossal standing wave, like those created when water swirls around a drain, but on a planetary scale. In lab experiments, swirling fluids can form similar polygonal shapes under the right conditions, hinting that Saturn's fast rotation and deep atmosphere might be sculpting this freak of nature. Yet, no model perfectly replicates the hexagon's razor-sharp edges or its mind-boggling endurance. Adding to the mystery is what lies at its center. NASA Cassini probe revealed a churning vortex inside the hexagon, resembling a towering hurricane with an eye 30 times larger than Earth's biggest hurricanes. But unlike earthly storms, this vortex doesn't disrupt the hexagon, it coexists with it, almost as if locked in an intricate dance. Some researchers speculate that the hexagon acts like a barrier, corralling the chaos within its geometric walls. Then there's the color. During Saturn's northern winter, the hexagon glowed an eerie blue, likely due to high-altitude haze clearing out. But as summer approached, it morphed into a golden hue, possibly from sunlight-driven chemical changes. These seasonal shifts suggest the hexagon isn't just a surface feature. It's deeply tied to Saturn's atmospheric chemistry and energy flows. Perhaps the most unsettling question is why we see nothing like it elsewhere. Jupiter's poles host sprawling clusters of cyclones, but none arrange themselves into perfect polygons. Neptune and Uranus have violent winds, but no geometric storms. Saturn's hexagon stands alone, a cosmic anomaly that challenges our understanding of fluid dynamics and planetary science. As we continue to study this marvel, one thing is clear: the hexagon isn't just a storm. It's a masterpiece of celestial mechanics, a reminder that even in the vastness of space, nature can produce wonders that feel almost designed. Up next, we'll delve into a darker cosmic theory, one that imagines a hidden companion to our Sun, a grim reaper lurking in the shadows of our solar system. Could the mythical Nemesis star be real? The evidence might surprise you. Now, let's turn our attention from the mesmerizing geometry of Saturn to a far more ominous cosmic possibility: the Nemesis star. This chilling theory suggests our Sun might not be alone in space. Lurking in the distant shadows of our solar system could be a dim, deadly companion, a star some have dubbed the Death Star for its alleged role in Earth's catastrophic past. The idea of Nemesis was first proposed in the 1980s to explain an eerie pattern in Earth's geological record. Roughly every 26 to 30 million years, our planet seems to endure mass extinctions, events so devastating they wipe out vast swaths of life. The most famous of these is the dinosaur-killing asteroid 66 million years ago, but evidence points to multiple such cataclysms spaced eerily evenly apart. Scientists wondered, could something be triggering THESE Chinese letter enter Nemesis? This hypothetical star, possibly a red dwarf or brown dwarf, would orbit the Sun at a staggering distance, up to 1.5 light-years away, far beyond the Oort cloud. Every 26 million years or so, as it swings closest to the Sun, its gravity would disturb the icy comets in the Oort cloud, sending a deadly rain of comets hurtling toward the inner solar system. This comet shower could explain not only the timing of mass extinctions, but also why impact craters on Earth and the Moon seem to spike during these periods. But here's where the theory gets controversial. Despite decades of searching, no one has found Nemesis. Infrared surveys like NAS, a wide-field infrared survey explorer, have scanned the skies for faint, cool stars, but none match the predicted profile. Some astronomers argue that if Nemesis existed, we would have spotted it by now. Others counter that brown dwarf stellar failures too small to shine brightly could still evade detection, especially if they're cloaked in dust or positioned in a tricky orbital plane. Then there's the problem of orbital stability. A star so far from the Sun would be easily tugged by passing stars or galactic tides, disrupting its SUPPOSED, Chinese letter, Chinese letter, Chinese letter, Chinese letter. Critics argue its unlikely Nemesis could maintain such a precise, long-term orbit without being thrown off course. Yet intriguingly, recent studies of distant solar system objects hint at gravitational anomalies clustering that might suggest an unseen, massive perturber, but whether it's Nemesis, a rogue planet, or something else remains hotly debated. Even if Nemesis isn't real, the theory has left its mark. It pushed scientists to consider how cosmic phenomena might shape life on Earth, from comet impacts to gamma-ray bursts. And it reminds us that our solar system story may still have hidden chapters, perhaps written in the dim glow of a forgotten sibling. Next up, we'll step away from cosmic doom and into a celestial phenomenon closer to home, a ghostly glow that has puzzled skywatchers for centuries. The zodiacal light, is it an illusion, or does it hold secrets about the dust that fills our solar system? Now, let's shift from the cosmic shadows of Nemesis to a subtler but equally mysterious glow in our own solar system, the zodiacal light. This ethereal phenomenon has been described for centuries, yet its true nature and origins continue to intrigue astronomers and stargazers alike. Picture this. You're in a dark, remote location after sunset or before dawn, and you notice a faint, pyramid-shaped glow rising from the horizon. Unlike the Milky Way's scattered stars, this light appears as a soft, diffuse cone, following the path of the ecliptic, the same plane where the Sun, Moon, and planets travel. Ancient civilizations often mistook it for the first light of dawn or a celestial omen, but we now know it's something far more tangible, yet no less fascinating. The zodiacal light comes from sunlight reflecting off countless tiny dust particles scattered throughout the inner solar system. These particles, some as small as grains of sand, form a vast, flattened cloud stretching from the Sun out beyond Mars. They're remnants of comets that have disintegrated over time, as well as debris from asteroid collisions. As sunlight hits these particles, it scatters, creating that ghostly glow visible under the right conditions. But here's where things get curious. Despite its delicate appearance, this interplanetary dust cloud holds clues to the solar system's violent history. Studies suggest that up to 30,000 tons of cosmic dust rain down on Earth every year, much of it part of this zodiacal cloud. Some of these particles even predate our solar system, carrying stardust from ancient supernova. Yet the cloud itself is far from static. Gravitational tugs from planets, especially Jupiter, constantly reshape its distribution, creating dense bands and gaps that astronomers are still mapping. One of the biggest puzzles is why the zodiacal light appears brighter than predicted. Recent missions like NASA's Juno probe have revealed that Mars may be contributing more dust than previously thought, possibly from its moon Phobos or even tiny, unseen satellites. Others speculate that interstellar dust particles from beyond our solar system might be mixing in, adding to the glow, For observers, catching the zodiacal light requires patience and perfect conditions. Light pollution is its greatest enemy, but in pristine skies, it's a sight that bridges the gap between the familiar and the cosmic. It reminds us that even the empty space between planets is teeming with hidden activity, a delicate tapestry of dust that connects us to the solar system's past. Next, we'll venture into one of cosmology's most mind-bending anomalies, a cold spot in the cosmic microwave background that might just be evidence of a parallel universe brushing against our own. Moving from the subtle glow of interplanetary dust, we now turn our attention to one of the most perplexing anomalies in the cosmos, a mysterious cold spot embedded in the afterglow of the Big Bang itself. This isn't just a minor temperature fluctuation. It's a vast, chilling void in the cosmic microwave background, the oldest light in the universe, and it might just be a window into realities beyond our own. Imagine the cosmic microwave background as a snapshot of the infant universe, taken when it was just 380,000 years old. This faint radiation fills the entire sky, a nearly uniform tapestry of microwaves with tiny temperature variations except for one region, about 1.8 billion light-years across, that's significantly colder than its surroundings. Dubbed the cold spot, this anomaly defies straightforward explanations. At first, astronomers thought it might be an observational error or a foreground effect, but repeated studies confirmed it's real. So what could cause such a drastic deviation? One leading theory suggests the cold spot is a supervoid, an enormous, nearly empty region of space where matter is unusually sparse. In such a void, light from the cosmic microwave background would lose energy as it traverses the underdense region, a phenomenon known as the integrated Sachs-Wolf effect. This would explain the cooler temperature, but here's the catch: the cold spot is far larger and colder than any known void should be. Surveys like the Dark Energy Survey have mapped the area and found some underdense regions, but nothing extreme enough to fully account for the anomaly. This discrepancy has sparked even wilder ideas. Some physicists propose that the cold spot could be evidence of a cosmic collision, a bruise left by our universe brushing against another bubble universe in a vast multiverse. According to this theory, the energy released during such an encounter could have created a localized disturbance in the cosmic microwave background, leaving behind this eerie cold patch. While speculative, the idea isn't entirely fringe. The multiverse is a natural prediction of certain inflation models, and if true, the cold spot might be our first tangible clue to its existence. Yet skeptics argue for more mundane explanations. Could it be a statistical fluke, a rare but natural outlier in the cosmic microwave background? The odds are slim. Calculations suggest there's only a 2% chance such a feature would appear randomly, but not impossible. Others propose exotic physics, like dark energy interacting differently in this region or primordial magnetic fields leaving an imprint. For now, the cold spot remains an enigma, a cosmic Rorschach test inviting us to project our boldest theories onto it. Whether it's a sign of parallel universes, an unseen void, or something even stranger, it challenges our understanding of the universe's structure and origins. As telescopes grow more powerful, future observations may finally unravel its secrets. Until then, it stands as a humbling reminder of how much we still don't know about the cosmos and how thrilling it is to explore the unknown. Now, let's shift our gaze from the eerie coldness of cosmic voids to something far more dynamic: stars that defy the very gravity of our galaxy. These aren't your typical celestial wanderers. Hypervelocity stars are cosmic projectiles, hurtling through space at speeds so extreme they're destined to escape the Milky Way entirely. Picture a star, often massive, blazing hot, catapulted from the heart of our galaxy at over 1 million miles per hour, fast enough to cross the distance between New York and Los Angeles in just 5 seconds. How does something so colossal achieve such blistering speed? The answer lies in the chaos of the galactic center. Most hypervelocity stars trace their origins to a close encounter with the supermassive black hole at the Milky Way's core, Sagittarius A star. When a binary star system drifts too close, the black hole's monstrous gravity can tear the pair apart. One star gets captured in a tight orbit, while the other is flung outward at incredible velocity, like a slingshot releasing its projectile. This dramatic ejection, known as the Hill's mechanism, was first proposed in the 1980s, but it wasn't until 2005 that astronomers confirmed their existence with the discovery of a star racing away at nearly 1.5 million miles per hour. But not all hypervelocity stars come from the galactic center. Some may be survivors of dwarf galaxies torn apart by the Milky Way's gravity, their stars scattered like debris from a cosmic collision. Others could be the result of supernova explosions in binary systems, where one star detonates and violently propels its companion outward. The variety of origins adds layers to the mystery, making each hypervelocity star a potential clue to different astrophysical processes. Detecting these runaway stars is like finding needles in a galactic haystack. They're rare, only a few dozen have been confirmed so far, and their extreme speeds mean they often traverse regions with sparse reference points, making their trajectories harder to track. Yet their journeys are invaluable. By studying their paths, astronomers can map the Milky Way's gravitational field and even probe the distribution of dark matter, which tugs at these stars in invisible ways. One of the most famous examples is LP 401-83-4035, a massive star ejected toward the outskirts of the galaxy. Observations suggest it might have originated not from the center but from a dwarf galaxy merger, hinting at the Milky Way's violent history of galactic cannibalism. Then there's US 708, a hypervelocity star so fast it's already left the galaxy's gravitational grip, destined to drift alone through the intergalactic void. The existence of these stellar speed demons challenges our understanding of galactic dynamics. They remind us that the cosmos is anything but static. It's a place of violent interactions, gravitational games, and celestial escapes. As telescopes like Gaia continue mapping stellar motions with unprecedented precision, more of these outliers will surely emerge, each carrying secrets about the forces that shape our galaxy. For now, they stand as breathtaking reminders that even in the vastness of space, gravity's grip isn't always absolute. Now, let's turn our attention to a celestial oddity so strange it sounds like science fiction, the Thorne-Zytkow object. Picture this, a star within a star, a cosmic Russian nesting doll where a red supergiant, one of the largest stars in the universe, swallows a neutron star, the densest known stellar corpse. This bizarre hybrid, first proposed by physicists Kip Thorne and Anna Zytkow in the 1970s, defies conventional stellar evolution. At its heart lies a neutron star, a city-sized remnant of a supernova, packing more mass than our Sun into a sphere just 12 miles wide. Normally, neutron stars exist as isolated pulsars or in binary systems, but in this scenario, one gets engulfed by a massive companion. Instead of being torn apart, the neutron star sinks to the core of the supergiant, where it orbits like a ticking time bomb. The outer layers of the red supergiant, bloated and turbulent, hide this dense intruder, creating a star with a neutron heart. What makes Thorne-Zytkow objects so fascinating is their potential to forge elements in ways ordinary stars can't. The neutron core's intense gravity and the supergiant's nuclear furnace could produce exotic isotopes of lithium, rubidium, and molybdenum through unusual fusion pathways. These chemical signatures, detectable in a star's spectrum, would be the smoking gun confirming their existence. Yet, despite decades of searching, no definitive candidate has been found. The closest astronomers have come is HV 2112 in the Small Magellanic Cloud, a star with unusual abundances of heavy elements. Initially hailed as a potential Thorne-Zytkow object, further studies revealed its odd chemistry might stem from a merger with a white dwarf instead. The hunt continues, with telescopes scrutinizing other red supergiants for similar anomalies. Why are these objects so elusive? For one, they're likely rare and short-lived. A neutron star spiraling into a supergiant would eventually destabilize its host, triggering a supernova or a gamma-ray burst. Plus, their outer layers mask the neutron core's presence, making them nearly indistinguishable from normal red supergiants unless we catch their unique chemical fingerprints. The existence of Thorne-Zytkow objects would revolutionize our understanding of stellar life cycles. They'd prove that stars can evolve in wildly unexpected ways, merging not just as black holes or neutron stars but as layered hybrids. Until we find one, they remain a tantalizing what-if at the frontier of astrophysics, a reminder that the universe still holds wonders we've only begun to imagine. As we push the limits of observational technology, each new survey brings us closer to solving this decades-old puzzle. Whether these stellar chimeras are confirmed or forever remain theoretical, they challenge us to rethink the boundaries of cosmic possibility. Now, let's flip the script on one of the universe's most enigmatic objects, black holes, by exploring their hypothetical opposite, white holes. If a black hole is a cosmic trapdoor where matter and light vanish forever, a white hole would be its mirror image, a celestial fire hose blasting energy and matter outward at the speed of light. Born from the same equations of general relativity that predicted black holes, white holes emerge as a tantalizing what-if in theoretical physics. The idea stems from the mathematical symmetry of Einstein's equations. Just as black holes form when matter collapses into an infinitely dense singularity, white holes would theoretically reverse the process, erupting from a singularity to expel material into space. Imagine hitting rewind on a black hole's life cycle. Instead of pulling everything in, it violently pushes everything out. Some theories even suggest white holes could be the other end of a black hole's tunnel, spewing matter into another universe or a distant region of our own. But here's the catch. While black holes have been observed indirectly through their gravitational effects and the fiery accretion disks around them, white holes remain purely hypothetical. No observational evidence has ever confirmed their existence. For one, they defy the second law of thermodynamics, which states entropy, a measure of disorder, always increases over time. A white hole's explosive output of perfectly ordered energy would essentially reverse entropy, making it a statistical improbability in our universe. Another hurdle is stability. Black holes form naturally from dying stars, but white holes would need to emerge from singularities already in place, essentially uncollapsing against gravity's pull. Most physicists argue this process violates known physics, as singularities aren't thought to spontaneously reverse their collapse. Even if a white hole did form, it would likely collapse back into a black hole instantly under the weight of its own gravity. Yet the concept isn't entirely dismissed. Some cosmologists speculate that the Big Bang itself could have been a white hole event, a primordial outburst of space-time and matter. Others propose that tiny, quantum-scale white holes might explain mysterious high-energy cosmic phenomena like gamma-ray bursts or fast radio bursts. There's even a fringe idea that dark matter could consist of ancient white holes, frozen relics from the early universe. The search for white holes remains a mix of mathematical curiosity and observational dead ends. Unlike black holes, which leave shadows in space-time, white holes would be far harder to spot. Their outbursts might resemble supernova or quasars, but without a clear signature to distinguish them. For now, they live on as a fascinating thought experiment, a reminder that the universe's rulebook might still have pages we haven't read. As we push the boundaries of physics, from quantum gravity to multiverse theories, white holes challenge us to rethink the limits of cosmic possibility. Whether they're ever found or remain forever in the realm of theory, they prove that even the wildest ideas can reshape our understanding of reality. Now let's venture into the bizarre quantum realm, where even empty space isn't truly empty. Quantum vacuum fluctuations are one of the strangest phenomena in physics. Tiny, fleeting bursts of particles and antiparticles that pop in and out of existence everywhere all the time. Imagine the universe as a bubbling cosmic soup, with these unpredictable particle pairs appearing and vanishing in fractions of a second. It sounds like science fiction, but it's a proven cornerstone of quantum mechanics, with mind-blowing implications for dark energy and the ultimate fate of the cosmos. The concept stems from Heisenberg's uncertainty principle, which states that energy can fluctuate unpredictably on the smallest scales. These fluctuations create virtual particles, pairs like electrons and positrons, that borrow energy from the vacuum of space, only to annihilate each other almost instantly. Though they exist for mere moments, their effects are measurable. For instance, the Casimir effect shows how two metal plates placed extremely close together in a vacuum are subtly pushed together by the pressure of these particle bursts outside the plates. It's as if the universe itself is fizzing with invisible activity. But here's where things get even wilder. Some scientists speculate that this quantum froth could be the key to understanding dark energy, the mysterious force accelerating the universe's expansion. The vacuum isn't just empty, it's brimming with this latent energy, often called zero-point energy. Calculations suggest the energy density of these fluctuations should be enormous, potentially driving the universe apart. Yet there's a glaring problem. Observed dark energy is far weaker than quantum theory predicts. This discrepancy, known as the cosmological constant problem, remains one of physics' biggest unsolved puzzles. One theory suggests that quantum fluctuations might operate differently on cosmic scales, cancelling out in ways we don't yet grasp. Others propose that undiscovered fields or dimensions could be tempering their effects. If we crack this mystery, it could redefine our understanding of gravity, space-time, and even the universe's fate. Will these fluctuations keep driving expansion until galaxies are ripped apart in a big rip? Or could they suddenly reverse, collapsing everything back into a singularity? Quantum vacuum fluctuations aren't just theoretical quirks, they're also being harnessed in cutting-edge tech. Researchers are exploring vacuum energy for futuristic propulsion or energy extraction, though the challenges are staggering. For now, these tiny, ghostly particles remind us that the universe is far stranger than it appears, and the answers to its biggest questions might be hiding in the flickering shadows of empty space. Now, let's shift our gaze to a theory that sounds like it's straight out of a sci-fi epic: galactic superwaves. These are hypothesized tsunamis of cosmic rays, bursting from the center of our Milky Way and sweeping across the galaxy at unimaginable speeds. Could they be responsible for past mass extinctions or even shaping the course of life on Earth? The idea is as thrilling as it is contentious, sparking fierce debates among astronomers. The concept was first proposed by physicist Paul Laviolette, who suggested that the Milky Way's core, home to a supermassive black hole, might periodically unleash shockwaves of high-energy particles. These superwaves would travel outward, packing enough punch to disrupt planetary atmospheres and trigger catastrophic climate shifts. Evidence for this comes from ancient ice cores, which show sudden spikes in cosmic ray activity coinciding with periods of mass extinction, like the one that wiped out the dinosaurs. But here's the catch: mainstream science remains skeptical. Many argue these events could be explained by nearby supernova or solar flares without invoking galactic-scale explosions. What makes superwaves so fascinating is their potential frequency. Some theorists claim they recur every 10 to 15,000 years, aligning with Earth's cyclical ice ages and cultural myths of apocalyptic floods. Proponents point to radioactive isotopes like beryllium-10 in geological layers, which hint at repeated cosmic bombardments. Yet critics counter that the data is too sparse to confirm a pattern, and the mechanism for such regular eruptions remains unclear. Could the Milky Way's black hole really hiccup on a schedule? The implications are staggering. If superwaves are real, they'd rewrite our understanding of galactic ecology. Planets would need protective magnetic fields or thick atmospheres to shield life from these periodic barrages. It also raises eerie questions about humanity's past. Could ancient civilizations have been toppled by cosmic radiation? Some researchers even speculate that superwaves might explain the mysterious Younger Dryas cooling event 12,000 years ago, which coincided with the disappearance of megafauna and early human cultural shifts. Today, the hunt for proof continues. Projects like the IceCube Neutrino Observatory in Antarctica monitor cosmic rays for unusual activity, while space telescopes scrutinize the galaxy's core for signs of impending outbursts. Whether superwaves are fact or fiction, they remind us that the cosmos is anything but quiet. The universe doesn't just whisper, it sometimes roars. And if these waves are real, the next one could already be racing toward us, invisible but inevitable, a silent tsunami from the heart of the galaxy. Turning our attention from the explosive power of galactic superwaves, let's explore a concept that could rewrite our understanding of intelligent life in the cosmos: the search for Dyson spheres. Imagine a civilization so advanced it harnesses the entire energy output of its host star by constructing a colossal megastructure around it. That's the essence of a Dyson sphere, a hypothetical feat of engineering first proposed by physicist Freeman Dyson in the 1960s. The idea might sound like pure science fiction, but scientists are actively scanning the skies for signs of these alien power plants, and the hunt has yielded some intriguing candidates. The search hinges on a simple clue: starlight that behaves strangely. A Dyson sphere, or even a partial swarm of energy-collecting satellites, would absorb and reprocess a star's light, making it appear unusually dim in visible wavelengths while glowing faintly in infrared as the structure radiates waste heat. Astronomers have combed through data from telescopes like Kepler and WISE, flagging stars with these exact anomalies. One of the most famous examples is Tabby's star, which we covered earlier. Its erratic dimming sparked wild speculation about alien megastructures, though dust clouds now seem the more likely culprit. But Tabby's star isn't alone. In recent years, projects like Glimpsing Heat from Alien Technologies, or GHAT, have identified dozens of stars with excess infrared emissions. Among them is a curious object called VVVWIT-07, a star that dimmed by a staggering 80% before brightening again, with no clear natural explanation. Then there's the case of two stars in the Milky Way, located just a few hundred light-years apart, both emitting unusual infrared signatures. Could these be coincidences or evidence of civilizations tapping into stellar energy on an unimaginable scale? Skeptics, of course, urge caution. Natural phenomena like circumstellar debris disks or young stars still cooling from formation can mimic Dyson sphere signatures. Even something as mundane as a cloud of interstellar dust passing between us and a star could create false alarms. That's why researchers emphasize the need for follow-up observations, using tools like the James Webb Space Telescope to analyze these stars' light in finer detail. The goal isn't just to find infrared excesses, but to detect specific thermal patterns that would betray the presence of artificial structures. Beyond the technical challenges, the Dyson sphere hunt forces us to confront profound questions about the nature of intelligence. If such megastructures exist, they'd imply civilizations millions or even billions of years more advanced than ours, capable of feats we can barely imagine. And if we find nothing, that silence might be equally revealing, suggesting that technological civilizations either self-destruct before reaching this stage or avoid such conspicuous projects altogether. The search continues, blending cutting-edge astronomy with cosmic archaeology. Whether we uncover proof of alien engineers or simply deepen our appreciation for the universe's natural wonders, the Dyson sphere hunt reminds us that the cosmos is full of mysteries waiting to be decoded. Up next, we'll confront perhaps the strangest puzzle of all, a thought experiment so bizarre it challenges our very perception of reality. Now, shifting our gaze from the search for alien megastructures, we arrive at a thought experiment so peculiar it could reshape everything we think we know about existence itself, the Boltzmann brain paradox. Picture this: in the vast, chaotic expanse of the universe, what if self-aware consciousness could simply pop into existence out of random quantum fluctuations? No evolution, no history, just a lone brain or even an entire mind spontaneously assembling from the void, complete with false memories of a life that never happened. That's the unsettling premise of the Boltzmann brain, a concept that tests the limits of cosmology, philosophy, and our very sense of reality. The paradox traces its roots to the 19th century physicist Ludwig Boltzmann, who suggested that in an infinitely old universe, even the most improbable events must eventually occur. Fast forward to modern cosmology, and this idea takes a bizarre twist. If the universe is truly eternal or cyclic, random fluctuations in energy could, statistically, create fully formed, self-aware observers, Boltzmann brains, far more often than they'd produce entire worlds like ours. After all, conjuring a single brain requires far less energy and order than crafting an entire universe with galaxies, planets, and life. So why don't we see these disembodied minds everywhere? And worse, how do we know we aren't Boltzmann brains ourselves, mere fleeting aberrations in an indifferent cosmos? Scientists and philosophers have grappled with this paradox for decades, and it's more than just a mind-bending hypothetical. It challenges the foundations of how we interpret reality. If Boltzmann brains dominate the statistical landscape, then our cherished memories, the laws of physics, even the apparent age of the universe could be illusions generated by a momentary fluctuation. Some theories, like certain interpretations of quantum mechanics or the multiverse, inadvertently invite this problem by suggesting infinite possibilities. Others, like the idea of a universe with a definite beginning like the Big Bang, offer a potential escape by limiting the time available for such fluctuations to occur. But the debate isn't just academic. The paradox forces us to confront the reliability of our observations. If most observers in the universe are Boltzmann brains, then our own perception of cosmic order might be a statistical outlier, a fluke. This has led some researchers to argue that any cosmological theory predicting a flood of Boltzmann brains must be flawed, a criterion now used to test models of the universe's origins. Meanwhile, others propose that consciousness itself might be a fundamental feature of reality, preventing such random formations. The chilling elegance of the Boltzmann brain paradox lies in its simplicity. It doesn't require alien megastructures or hidden dimensions, just the raw statistics of chaos and time. Whether a profound truth or a cosmic red herring, it reminds us that the universe's greatest mysteries might not lurk in distant galaxies, but in the very nature of existence itself. And with that, we've reached the end of our journey through 50 of the cosmos' strangest phenomena. But as always, the universe keeps its deepest secrets close. As we draw the curtains on this cosmic journey through 50 of the universe's most baffling wonders, one thing becomes undeniably clear: the cosmos thrives on mystery. From the eerie silence of the Fermi Paradox to the ghostly whispers of dark matter, and from the fleeting brilliance of fast radio bursts to the mind-bending conundrum of Boltzmann brains, we've traversed a landscape where every answer seems to birth new questions. These phenomena aren't just quirks of nature, they're cosmic breadcrumbs guiding us toward deeper truths about reality itself. Think about it, for all our advancements, we've barely scratched the surface. Dark matter and dark energy alone make up 95% of the universe, yet we still don't know what they truly are. The Great Attractor tugs at galaxies like a hidden puppeteer, while rogue planets drift untethered through the void, challenging our definitions of a world. Even our own solar system holds puzzles, like the Saturn hexagon, a storm so precise it feels almost artificial. And let's not forget Tabby's star, whose flickering light sparked debates about alien megastructures before settling unsatisfyingly on dust. The universe, it seems, loves to keep us guessing, but that's the thrill of it, isn't it? Every mystery is an invitation to explore, to question, to wonder. Maybe you're captivated by the haunting beauty of the red rectangle nebula, or perhaps the chilling implications of the black hole information paradox keep you up at night. Whatever your favorite enigma, one thing unites them all. They remind us that curiosity is our greatest tool. The day we stop asking why is the day we stop understanding the cosmos. So what's next? The universe isn't done surprising us. New telescopes like the James Webb are peeling back layers of the unknown, while theories like quantum gravity inching us closer to unifying physics. Who knows, the next great cosmic revelation might be lurking in data we've already collected, waiting for a fresh pair of eyes to spot it. Or maybe it's something entirely unexpected, a phenomenon so strange it's not even on our radar yet. Before you go, let's keep the conversation alive. Drop a comment below telling us which of these 50 phenomena blew your mind the most. Was it the diamond planet, the phantom galaxies, or something else entirely? And if you're hungry for more cosmic mysteries, don't forget to hit that subscribe button and ring the notification bell. The universe is vast, and we've only just begun to explore its wonders together. Until next time, keep looking up and never stop wondering. The greatest discoveries, after all, start with a single question.